Welcome to AP Chemistry Review and Practice. My name is Michael Faribaugh, and I'll be your guide on the side as you strive toward that 5 on the AP Chemistry exam. Each episode will include answers and explanations to practice problems, along with advice to help you avoid common mistakes. So, are you ready to review and practice for the AP Chemistry exam? I hope so, because this lesson starts right now. Welcome back to AP Chemistry Review and Practice. In this final episode before the AP exam, I will share my last-minute tips and strategies for how to answer free response questions. You can add your comments and questions below this video, and you can also email me with your comments and questions at apchemistryreviewandpractice@gmail.com. Check out the links in the video description area, which include the link to a Google folder that contains AP Chemistry free response questions and scoring guidelines from previous years. Okay, let's get started. We will begin with Unit 1. Our first question, which comes from the 2025 AP Chemistry exam, says an incomplete mass spectrum for magnesium is shown in the diagram. The percent abundance of magnesium-24 is 79%. The percent abundances of the other two natural isotopes of magnesium, magnesium-25 and magnesium-26, are approximately equal. So if we know that 79% subtracted from 100 would give us 21%, and that has to be split evenly among these two isotopes. 21 divided by 2 is 10.5. Here's what we have to do. Complete the mass spectrum by drawing thick lines in the appropriate locations to represent the percent abundance of magnesium-25 and magnesium-26. So in this video, I will show you lots and lots of examples of incorrect student responses. I will explain why that particular response is incorrect, and hopefully at the end of this lesson, you'll get really good advice about how to avoid making those types of mistakes when you take the free response section of the AP Chemistry exam. So we know that we have to draw 2 lines for 10.5%. So can you see the student's mistake? They thought they were drawing the percent abundance of 10.5%, but they didn't pay attention to the scale on the y-axis. So those lines are halfway between 10 and 20, and that means they look like 15%, which is incorrect. So this response would not earn the point. Here is the correct diagram that should be drawn from the official scoring guidelines for this question. The abundance for the 2 lines should be between 10 and 11. Now, in our next question, which also came from the 2025 AP Chemistry exam, it says that a student combusts a sample of ascorbic acid, which we don't know exactly what that chemical formula is, so it says CXHYOX, to determine its chemical composition. The only products of the reaction are 0.2400 mole of carbon dioxide and 2.883 grams of water. So the first part of this question is to calculate the number of moles of water produced. Now, I don't have a problem or a mistake with what the student did so far. They went from grams to moles using the information on the periodic table to determine the molar mass of water. So far, everything looks good. Now it says that the mole ratio of carbon to oxygen is 1:1 in ascorbic acid. Now, based on this information and your answer to the first part of the question, determine the empirical formula of ascorbic acid. So here's what the student did. They said we have moles of carbon, moles of hydrogen, moles of oxygen, and the 0.24 came from the moles of carbon dioxide. 0.24 moles of carbon, and then based on that fact that carbon and oxygen have that same 1:1 ratio, this is what they have. 0.24 for both carbon and oxygen, and if you're wondering, where did that 0.16 come from in the middle? Well, that was their assessment of the amount of moles of hydrogen. So what they got was a 3:2:3 ratio. Now, hopefully you can see the student's mistake. There are 0.1600 moles of water, but the student forgot to multiply by 2 to go from moles of water to moles of hydrogen. So that's an important detail. Make sure you realize that there are 2 moles of hydrogen atoms for every 1 mole of water. So the correct answer to that question is not C3H2O3, but rather C3H4O3. And again, all of these questions are from previously released AP Chemistry exams, so you have access to all of the questions and the scoring guidelines in that Google folder that is linked in the video description area. All right, for our next question, this came from the 2023 AP Chemistry exam. All we have to do is write the complete electron configuration for an atom of manganese. Now, manganese has a total of 25 electrons, so the student wrote the following: 1s2, 2s2, 2p6, so that would be 10 electrons. 3s2, 3p6, now that brings our total to 18 electrons. And then finally, 4s2, and the student wrote 4d5. So the mistake that they made is in that D sublevel, that should be 3d, not 4d. So the correct answer is 1s2, 2s2, 2p6, 3s2, 3p6, that was fine, but then 4s2, 3d5. Moving on, the next part says that when manganese forms cations, electrons are lost from which subshell first? So all we have to do is identify both the number and the letter associated with the subshell in which the electrons are lost from an atom of manganese. And the student wrote 3d. And again, that's a mistake because we should always lose the electrons from the valence s orbitals for a transition metal. So that actually should be 4s, in which the electrons are lost, not 3d. So the correct answer is 4s. In our next part of this question, it says a student performs an experiment to produce a manganese salt. Now, we don't know the chemical composition. It's MnXCl. There was a chemical reaction in which the manganese reacted with a sample of hydrochloric acid, and now we have this MnXCl, which is a solid. So this part of the question says, calculate the mass of chlorine in the sample of MnXCl solid remaining in the beaker. So what did the student do? Well, they took 2 numbers from the table and they subtracted them, and they got 2.504. Can you see what they did that was incorrect? They picked 2 numbers from the table, but unfortunately they picked these numbers. Those numbers would be the mass of the empty beaker and the mass of that solid manganese chloride compound at the end of the experiment. So if we subtract those numbers, we do not get the mass of chlorine, we get the mass of the solid in the beaker at the end of the experiment. So considering that the middle row of that table says mass of beaker and manganese, these are the 2 numbers that we should have subtracted. So that difference would represent the additional amount of chlorine that is now present in that compound at the end of the experiment. So that is the correct answer. And now we're going to do something with 1.411 grams of chlorine atoms. So calculate the number of moles of chlorine in the sample. So here's what the student did. They looked on the periodic table. They found the atomic mass or the molar mass of Cl, which I believe is 35.45 on the periodic table, and they wrote this for their answer. Now, it's not that their answer numerically is incorrect, but they would not earn credit for their response. Why? Because they didn't show any work. So they did calculate the correct value for the number of moles of Cl, but because they didn't show any of their work, they did all the work on their scratch paper or on their calculator, they would not receive credit. So again, everything in this video lesson are going to be hopefully examples of good advice to help you avoid making these sorts of mistakes, and then that way you can earn the maximum number of points possible on the free response section of the AP Chemistry exam. So always show your work for your calculations. Now, moving on to the next part, they took that number of moles of Cl and they connected that to the number of moles of manganese. So we are told in the next part of the question that 0.0199 moles of manganese was consumed in this experiment. So now we have to connect the number of moles of Cl that we just calculated in the previous part of the question to the number of moles of manganese. And this is what the student did. They recognized that there is a 2-to-1 ratio, and so they wrote an empirical formula of this compound. Now, take a look at what they wrote. Can you see their mistake? Well, they knew it was a 2-to-1 ratio. Unfortunately, it's a 2-to-1 ratio of chlorine to manganese. So by writing Mn2Cl, they would not earn the point for their response because they put the 2, the subscript, in the wrong place. The correct answer is actually MnCl2. Again, I'm giving you these types of examples to help you avoid making either careless errors or other types of situations where you don't show your work or you make some sort of error in the calculation. So pay attention, be careful, and read the question carefully. All right, this is a new question from the 2021 AP Chemistry exam, and what we are looking at is an incomplete or a partial photoelectron spectrum for silicon. And so what we have to do to answer this question is on the spectrum, we have to draw the missing peak that corresponds to the electrons in the 3p sublevel. Now, when I look from left to right, where highest binding energy is on the left, and then I move from left to right, the binding energy decreases, we start with 1s. So 1s on the left, and then 2s and 2p. This is what the student wrote for silicon. Well, if you can't see the student's mistake, it turns out that what they wrote was 1s2, 2s2, 2p6, 3s2, and then finally 3p, they wrote 3p4. Now, the electron configuration of silicon, which has 14 electrons, would stop at 3p2. So they wrote that diagram peak too high. So they might have been thinking of sulfur instead of silicon or just not paying attention. So the correct answer is that that peak, which is located on the far right side of the diagram, looks more like this. So again, it should be 3p2. That peak should be drawn to the right of the other peaks, but it should reach the second line, indicating that that would be 3p2, not 3p4. So this is the correct answer to that question. All right, in our next example, it has to do with periodic trends. The question says, using principles of atomic structure, explain why the first ionization energy of germanium is lower than that of silicon. And here's what the student wrote for their answer. They said that germanium has more electrons and more orbitals than silicon. Germanium has a larger atomic radius than silicon, and so it's easier to remove electrons from germanium. Can you see the student's mistake? Did they use principles of atomic structure? And the answer is no. The student has mentioned periodic trends, but they did not give an explanation that uses principles of atomic structure. So what you should do is talk about the location specifically of the orbitals and the energy levels. So here is the official answer to this question. The valence electrons of a germanium atom occupy a higher shell, energy level 4, than those of a silicon atom, energy level 3. So the average distance between the nucleus and the valence electrons is greater in germanium than silicon. That's very complete and explains that you're talking about different energy levels, therefore weaker coulombic attractions for the germanium versus the silicon, easier to remove the electrons, therefore the ionization energy of germanium is less than that of silicon because those valence electrons in germanium are located in a higher energy shell or level, making them easier to remove. So my advice to you is that if you have to explain a difference between two elements that are located in the same group on the periodic table, you definitely want to talk about the difference in the energy levels of the outer shells or the valence shells for each atom. So don't just say more orbitals or more electrons. You can say a greater number of occupied energy levels or shells, but even better, specifically mention the different energy levels, whether that's energy level 2 or 3 or 4 when you're making that comparison. Now, for our next free response question, we will move from Unit 1 to Unit 2. So here is our next free response question. So in this question, which is from the 2025 AP Chemistry exam, it says identify the hybridization of the valence orbitals of the carbon atom in the H2CO molecule. Our only options for hybridization are sp, 2 electron domains, sp2, 3 electron domains, or sp3, 4 electron domains. And the student said the following. They said sp3, so it is possible that there's some confusion regarding the double bond. So the student may be confused about the distinction between electron pairs and electron domains. Around that carbon atom, even though there are 2 single bonds and 1 double bond, that would be 4 total electron pairs around that carbon atom, there's only 3 electron domains. So whether it's a single bond, a double bond, or a triple bond, that would count as a single electron domain. And there are no lone pairs of electrons on that carbon atom, so there's a total of 3 electron domains. The correct answer is actually sp2. All right, our next question, which is also from the 2025 AP Chemistry exam, has to do with geometry. It says, based on the VSEPR theory, predict the geometry around the silicon atom in compound Y. So looking at that silicon atom, I can see 4 single bonds to that silicon atom. This is what the student wrote. So unfortunately, this happens all the time on the AP Chemistry exam. So we're looking for a geometry which is trigonal planar or tetrahedral or linear or bent, but the student gives the bond angle instead. Now, we just had a question on hybridization. So obviously the mistake here is that they gave the bond angle when the question was asking for molecular geometry. Students sometimes give the hybridization instead of giving the molecular geometry. So what we're looking for is not 109.5 or sp3, we're looking for tetrahedral in this particular case. So there's the silicon with 4 single bonds, and they wanted the geometry. Again, just pay attention to the details. Bond angle, 109.5 or 120 or 180. Molecular geometry, seesaw or tetrahedral or trigonal pyramidal. And if they want the hybridization, sp, sp2, sp3. Just pay attention to those details. They are related to each other, but they're very different. And I want you to earn the point on the free response section when you get that question. All right, this next one looks like it might be about periodic trends, but it's actually about the definition of a certain type of alloy. So this is from the 2024 AP Chemistry exam. We are given a data table with silver and copper and the atomic radius. Explain why sterling silver is better classified as a substitutional alloy than as an interstitial alloy. They're not making you choose whether it's one type of alloy or the other. You have to explain why it is better classified as a substitutional alloy. And here's what the student wrote. They said silver has a larger radius than copper, and these 2 elements are metals located in the same group. Now that's all true, but they didn't actually answer the question. So the mistake in this case is that the student fails to account for the fact that sterling silver is better classified as a substitutional alloy. You have to talk about the fact that silver and copper have similar radii. Now you might say, but isn't 165 different than 145? Again, they told you it is better classified as a substitutional alloy. So you're not making that choice. You're simply showing the AP readers that you understand what a substitutional alloy is. So the official answer is the following. Silver and copper have similar radii. So the alloy would be substitutional versus interstitial. Now in this next question, which has to do with Lewis diagrams, we see a Lewis diagram that is completed on the left. Now if you're nervous about that single dot on the central nitrogen atom, it turns out that 6 valence electrons for oxygen, 5 valence electrons for nitrogen, that would be 6 plus 5 plus 6. So for the NO2 molecule, it contains an odd number of electrons. 6 plus 5 plus 6 is actually 17 electrons. here's what we have to do, which is the incomplete diagram on the right. In the box on the right, complete the Lewis diagram for the NO2 plus ion. Well, if you're not sure whether the NO2 plus means lose an electron or gain an electron, I will show you what the student did. So I see 17 total valence electrons on the left, and this is what the student wrote for their Lewis diagram. Now at first glance, yes, every atom has a complete octet, so that's good, but if you count the total number of valence electrons in that diagram, 2, 4, 6, 8, 10, 12, 14, 16, 18. So what did they do wrong? They added one electron instead of removing one electron from that total. So it's actually incorrect because it should be NO2 plus. That means it lost an electron. So it goes from 17 to 16, not 17 to 18. So here is the correct Lewis diagram, which contains 16 electrons. That Lewis diagram looks very similar to the carbon dioxide molecule. All right, now we have a follow-up question based on this Lewis diagram. You'll notice that these are slightly different from each other, and it says a student makes the claim that the bond angles in the NO2 molecule, which is on the left, and the NO2 plus ion, which is on the right, that these bond angles are different. Now, do you agree or disagree with the student's claim? Justify your answer. You do not get a point on the AP Chemistry exam for simply flipping a coin and saying agree or disagree. If you get the correct agree or disagree, but you don't justify your answer correctly, then you would lose the point for that question. So here we have justify your answer. The student said, I agree, as in the bond angles are different, because NO2 has one double bond and one single bond, which is on the left, whereas NO2 plus has two double bonds. Again, that's a true statement, but it's not the correct justification for the different bond angles. So look at the dot. Even though it's not a lone pair of electrons, it is still an electron domain on that central atom. So what did the student do that was incorrect? The student attributes the different bond angles to the difference in bonding rather than the presence of the lone electron on the central atom. So here is the correct answer to this particular question from the official scoring guidelines. They could either say one of the following. Yes, I agree, as in the bond angles are different because the angle of NO2 plus is different from the angle in NO2, because there would no longer be a non-bonding electron on the central atom in NO2, and the oxygen atoms would spread farther apart, forming a linear structure with a different angle of 180 degrees. I don't know what the bond angle is in NO2, but it's not 180 degrees. Another acceptable way of responding to this question is to focus on the hybridization, that the hybridization of the nitrogen in NO2 would have 3 electron domains, so sp2, and that would be approximately 120 degrees, whereas the hybridization in the NO2 plus ion with only 2 electron domains, that would be sp. So again, either of those are acceptable, but just to simply say that one has 2 double bonds and the other has a double and a single, that was an incorrect justification for the difference in the bond angles. All right, moving on to our next question. This relates to the bond length and the bond energy. So you've seen diagrams like this before. Read the question carefully because watch what happens. So in this question from the 2023 AP Chemistry exam, it says, what is the bond length in picometers for the Cl2 bond? And the student wrote 250. Now what they probably did is they looked at the wrong axis. The 250 would be kilojoules per mole. That's the bond energy. That's not the bond length. The bond length would be on the x-axis. So 200 picometers is correct, not 250, which is the bond energy. The follow-up question says a student finds that the average AlCl, so we're switching to a different bond, that length is 220 picometers, and that the average bond energy is 425 kilojoules per mole. This is the curve that the student drew. Now, at first glance, I see a bond energy that looks like it's somewhere between 400 and 450, so I like that. It's about 425 kilojoules per mole. But if you look closely at the x-axis, if you look at every little line on the x-axis, it would be every line on the x-axis is actually worth 20 picometers. So they didn't pay attention to the scale on the x-axis. Their bond actually looks like it would be 240 picometers. That's a very subtle mistake, and yet that student did not earn full credit for that drawing. So pay attention to the labels and the tick marks and the numbers on each axis, especially when you have to draw your own diagram. So the correct curve would still have a bond energy of 425 kilojoules per mole, but as you can see in this correct diagram, the bond length would be 220, and that's that first line, not what I've drawn here looks more like 240. So this is the correct diagram for a bond length of 220. All right, in our next question, this is from the 2023 AP Chemistry exam, I see 3 different Lewis diagrams. They're telling us that the AlCl3 molecule has trigonal planar geometry. Which diagram can be eliminated based on geometry? Now, when the AP Chemistry exam asks you to make a choice and they say based on, pay attention to that. We're not looking at other factors, we're just looking at geometry. So here's what the student said. And again, this is an incorrect answer. They said diagram 1 can be eliminated because Vesper theory only applies when each atom has a complete octet. So the reason that the student chose diagram 1 to be eliminated is they said that the aluminum atom doesn't have a full octet. Now, the question was talking about geometry, not the octet rule. So hopefully you can see that their mistake was that they should have chosen diagram 2, because if I look at that central aluminum atom, I see 3 single bonds and a lone pair of electrons. That's 4 electron domains. Now that molecule would be trigonal pyramidal geometry with 4 electron domains, 3 bonding, 1 non-bonding. So the correct answer is not diagram 1 based on the octet, but rather diagram 2 because it has 4 instead of 3 electron domains. So wrong geometry. Now, moving on to the next part of this question, it said which of the 3 diagrams, again, same diagrams as before, is the best representation for the bonding, and this is not about geometry. Now it says justify your choice based on formal charges. This is what the student said. Again, this is an incorrect answer. So they said diagram 1 is the best representation for the bonding. They said because aluminum has a charge of +3, and chlorine has a charge of -1, and the sum of all the charges in the diagram are equal to 0. Now, did that student talk about formal charges or something else? So the mistake here is that the student is probably confusing formal charge with oxidation numbers. They made the correct choice, but their justification is incorrect. If you're not sure about formal charges, you may have to review that. I will tell you that formal charges are valence electrons minus the sum of the dots and the bonds. So for aluminum, that would be 3 minus 3, 3 valence electrons and 3 bonds. And then for chlorine, that would be 7 minus, and there are 6 dots and 1 bond. So 7 minus 7 is 0. So the correct answer is diagram 1, but not with the formal charges that they had listed. This is the correct answer. All atoms in diagram 1 have a formal charge of 0, whereas in the other diagrams, 2 and 3, some of the atoms have non-zero formal charges. All right, before we move on to Unit 3, the last question I'm going to give you for Unit 2 is actually a multiple choice question. Now, I know I said that this lesson is all about free response questions, and it definitely is, but here's another example of read the question carefully. So the student chose choice B. Now, it is true that the fluorine is more electronegative than bromine, and bromine is more electronegative than iodine. So looking at choice B, there is definitely a ranking of the polarity of the bonds. But the mistake is that they didn't read the question carefully, and so HI is actually less polar than HBr, and HBr is less polar than HF, so they picked a choice in which the bonds are arranged in order of increasing polarity. But the question asked for decreasing polarity. So we have to start with the most polar bond first and the least polar bond last. So the correct answer was actually A. So again, read the question carefully is something I've said all season long in this series of lessons, AP Chemistry Review and Practice. All right, well, that was the last question for Unit 2. So our next free response question will have to do with Unit 3. So the question that we are about to see, which comes from the 2025 AP Chemistry exam, falls under topic 3.1, intermolecular and interparticle forces. So in this question, it says the particle diagram shown represents a magnesium ion in beaker 1. A sodium ion in beaker 2 has a weaker attraction to water than the magnesium ion does. Explain this phenomenon using Coulomb's law and each of the following. Now notice that we're not making a prediction about which ion has a stronger or a weaker attraction to water. They told us that sodium, the Na plus ion, has the weaker attraction to water than the magnesium ion does. So make sure that you don't simply restate the information that was already given to you in the question. And because Coulomb's law involves both the charge on the ions as well as the distance or the radii or the size of the ions, then we have to consider each of these factors. So, relative charge. Here's what the student said. The sodium ion has a weaker attraction to water because sodium is +1 and magnesium is +2. Now, on the AP Chemistry exam, you will not earn credit for simply restating information that was already given to you in the question. So the mistake here is that the student simply restates information that is already given in the question. They list the charges on the ions. Sodium is +1, magnesium is +2, but they don't actually compare the charges on the ions. So I'll talk about that in the official scoring guidelines answer, which I will show you in just a moment. Now, with respect to the radii, the student said that the sodium ion is larger than the magnesium ion. Now that's good. That's part of what they should say. But they say, so the nucleus has a weaker pull. Now what they're actually talking about is the attraction of the nucleus to the valence electrons. But the particles that we should be considering are not electrons and the nucleus, but rather the ion and a nearby water molecule. So the mistake here is that the student correctly states that sodium is larger than magnesium, but refers to the pull of the nucleus. Well, the pull of the nucleus on what? On the electrons in the ion or on something else, which is not part of the ion, but this other water molecule. And the fact that the student does not mention the larger distance between the ion and water, again, it says very clearly attraction to water. It doesn't say attraction to electrons. It says attraction to water, and we've got a nice particle diagram. We can see that an ion is surrounded by water molecules. So here are the official scoring guidelines for this question, which appeared on the 2025 AP Chemistry exam. So the part about the charge on the sodium ion is less than the charge on the magnesium ion, which again, based on Coulomb's law, would result in a smaller charge and a weaker Coulombic attraction between the sodium ion and water. We're not talking about electrons here, we're talking about the sodium ion and nearby water molecules. Again, don't just list the charges, but compare the charges. And then as far as the size, the sodium ion is larger than the magnesium ion, so the distance between the sodium ion and the water molecule will be greater. So it's not about the distance, in this case, between the nucleus and the valence electrons. Now, if this was about ionization energy, then yes, you would definitely be considering the attraction between the nucleus and the outer electrons. But here, it's about the water molecule, so it's about the distance between the ion and the nearby water molecules. All right, let's move on to our next free response question. So this one says, calculate the concentration of the magnesium ion after the two solutions are combined. Now, there is a solution on the left, which has a volume of 35 milliliters. There's a solution on the right, which has a volume of 50 milliliters. And these two solutions will be combined together in beaker 3, according to the information in the diagram. So the student correctly set up an equation for calculating the concentration of the magnesium. I see 1.85 times 10 to the negative 3. That is the concentration of the magnesium nitrate, which is the solution in beaker 1 on the left. And then we don't know the concentration of the magnesium in beaker 3, so they have 35 milliliters. That looks good. Ah, do you see the mistake? What is the total volume when these two solutions are combined together? 35 plus 50 is actually 85. So what they should have done in their M1 V1 equals M2 V2 is use the total volume of the solution in the setup for this calculation. So the total volume is not 50, the total volume is 35 plus 50, which is 85. So the correct answer is 7.62 times 10 to the negative 4 moles per liter. And you can see this is the correct setup with 35 milliliters on the left side of the equation and 85 milliliters on the right side of the equation. So just be careful that if you have a lot of numbers that are given to you in a problem, that you use the correct value if you're doing a dilution calculation like this. All right, now our next one, we're going to go back to attractive forces between particles. We've already looked at ion dipole attractions. So in other words, the attraction between ions and polar water molecules. Now I see several molecules in this diagram. We have a mixture of CH3OH and H2CO. And the question says we have to draw a single dashed line, which means don't draw 2, don't draw 3, just draw 1, to represent a strong hydrogen bonding attraction between one molecule of CH3OH and one molecule of H2CO. So for this question, because we're focusing on the mixture of two different substances, it would be incorrect to draw a line between two of the same molecule. Just read the question carefully. Now, here's what the student drew in terms of their hydrogen bonding attraction between one CH3OH molecule and one H2CO molecule. So I'll give you time to think about that. They definitely have an oxygen on the CH3OH molecule connected to a hydrogen on a different molecule. But remember that for a molecule to participate as a hydrogen bond donor in a hydrogen bonding attraction, the hydrogen atom must be bonded directly with either nitrogen, oxygen, or fluorine. Now, the other atom, which is the hydrogen bonding acceptor, that atom, nitrogen, oxygen, or fluorine, does not need to be directly bonded to hydrogen. So looking at the H2CO molecule, it's fine to use that oxygen, but the hydrogen is directly bonded to carbon, so that's the problem. So in this diagram, I have put red squares around the only two hydrogen atoms that can participate as a hydrogen bond donor in this interaction. So this would be correct. Again, look at that molecule of H2CO. I don't need that oxygen, the one that's the hydrogen bond acceptor. I don't need that atom to be directly bonded to hydrogen. I need the donor to be a hydrogen atom that is directly bonded to either N, O, or F. With the acceptor, I just need the N or the O or the F to be part of a polar bond. And in the CO double bond, that oxygen is part of a polar bond, and that would be a hydrogen bonding acceptor. Another possible answer to this question could have been this one. Again, kind of reaching out there to that oxygen on that H2CO molecule. And again, the hydrogen on the CH3OH molecule, that is an acceptable hydrogen bonding donor because the hydrogen is directly bonded to the oxygen. All right, in our next question, it says a student claims that compound Y, which is located in the table on the right, has a higher boiling point than compound X. Well, we can see that information. 98 degrees Celsius is the boiling point of compound Y. 82 degrees Celsius is the boiling point of compound X. So we're not making a prediction. They're giving us the data. We have to come up with a reason why. So the student claims that the compound Y has the higher boiling point because compound Y has stronger London dispersion forces. Do you agree or disagree? Justify your answer. So you cannot simply say, I agree, and then that's it. You also can't say, I agree, yes, it does have stronger London dispersion forces, because now you're just restating what was already mentioned in the question. So here is what the student wrote. I agree, compound Y has stronger London dispersion forces, and this was their justify your answer. They said because silicon has more electrons than carbon does. Now, they're not wrong. Silicon definitely has more electrons than carbon. However, this answer says nothing about whether you understand what London dispersion forces actually are. So you may know there's a word that is often used with London dispersion forces, and that word is polarizable or polarizability. So this question is checking to see if you understand how London dispersion forces between molecules work. So the problem is that the student only mentioned more electrons, but they didn't mention that this compound Y has a more polarizable electron cloud. So more electrons was not a sufficient justification with respect to London dispersion forces. Here is the official scoring guidelines answer. So yes, I agree with the student's claim that compound Y does have stronger London dispersion forces, and it's because compound Y has a larger, and there's that phrase, more polarizable electron cloud, because the silicon atom has more occupied electron shells than the carbon atom. Again, that's true because silicon is 1s2, 2s2, 2p6, and then we keep going 3s2, 3p2. That's the third energy level, whereas carbon stops at 1s2, 2s2, 2p2. So that's all true. Again, more electrons or more occupied electron shells was not enough. The phrase more polarizable electron cloud was essential for this question. So again, stronger London dispersion forces was already stated in the claim. More electrons is not enough. More polarizable electron cloud. All right, let's go ahead and take a look at our next question. This question from the 2024 AP Chemistry exam has to do with a molarity calculation. Now, this is not M1V1 equals M2V2. We're not doing a dilution. We are simply dissolving 10.22 grams of sodium hydroxide, molar mass 40 grams per mole, in water to produce 500 milliliters of solution. Now, in my classroom, I tell my students all the time, I would love it if you would put units in your scratch work as you're setting up your calculation. Now, some students think, well, is that because the AP exam will not give me credit if I don't put units? It turns out that we still give credit on the AP Chemistry exam for a student who shows their work without putting all of the units in their scratch work. But here is why I think it's a good idea to show units in your scratch work. It helps you remember what you're doing. So when you include units in the setups for your calculations, it will remind you, wait, is this joules or kilojoules? Is this milliliters or liters? Is this grams or moles? And when you don't put any units, you might forget what you're doing in the middle of your calculation. So did this student go from grams to moles? Well, I see 10.22 divided by 40. So I see 10.22 divided by 40 with no units. And then they divided by 500. So the mistake here is they successfully calculated the number of moles of sodium hydroxide, but instead of dividing by the volume in liters, they divided by the volume in milliliters. So the setup for the mole calculation is correct, but they divided by 500 instead of dividing by 0.5 liters. So again, my advice to you is try to put units in your scratch work, not because you're trying to show off for the AP readers, but it actually helps you avoid making some careless errors. So units are good because the units will remind you what you are doing in the middle of a calculation. All right, let's go ahead and take a look at our next example. This one has to do with the ideal gas law. And the reason why we know this has to do with the ideal gas law is because if you are given 3 of the 4 variables in the ideal gas law, you can solve for the one that you don't know. And those variables are P for pressure, V for volume, N for number of moles, and T for temperature. So in this question from the 2024 AP Chemistry exam, it says calculate the volume of the carbon dioxide gas in liters. So I'm going to rearrange the ideal gas law, solve for volume. And I can see in this problem that they're telling us we have 0.0114 moles of carbon dioxide. So that would be the N in the ideal gas law. There's no units in this setup. Okay, there's probably going to be an issue here with some sort of lack of units here. So I'll go ahead and take a look at the pressure is 1.25 atmospheres. So that would be the P on the bottom. Now, should those temperature units be in Celsius or Kelvin? Definitely Kelvin. So 20 Celsius is incorrect. 20 plus 273, that would be 293 Kelvin. And what is that 8.314? What is that doing there? Well, apparently there is more than one value of the ideal gas constant. So back to my comments about units. We want atmospheres. We're not ready to do joules. That's thermodynamics. That would be unit 9. So we want 0.08206, which has units of liters, atmospheres, Kelvin, and mole. Oh, look at those lovely units. I've got the moles, and those will cancel out. I've got the Kelvin, and those units will cancel out. The atmospheres cancels out. So the correct answer numerically is 0.219, but we can see very clearly that it's also going to be units of liters. Now, do you have to make it look this pretty, this special on the AP Chemistry exam when you set up your calculation? No. But it's a nice idea to remind yourself what you're doing in the middle of a calculation. So I will continue to talk about units as often as I can. All right, let's go ahead and move on to our next question. This has to do with a chromatography experiment. Now earlier we did a solution calculation involving M1V1 equals M2V2. That was a dilution. We also did a calculation in which we were given the grams and we were given the volume and we had to calculate the molarity. In this question, we are given the molarity, which is 0.340 moles per liter of sodium chloride. We're also given the volume of 100 milliliters, and we have to calculate the mass in grams. Let's see if the units are used appropriately in the setup. Oh my goodness gracious. This student has 0.34 with no units, multiplied by 58.44 with no units, and then magically they have 19.9 grams. Hopefully you can find out the mistake here. Now normally it is volume times molarity equals moles. I don't see volume at all in this calculation. I see molarity times molar mass. So the student multiplied the molarity by the molar mass, but what they should have done initially is to set up volume times molarity to get moles, and then continue with moles times molar mass to get grams. So their incorrect answer was 19.9. The correct answer is actually 1.99. So the difference is that now we have 100 milliliters or 0.1 liters times the molarity. So now you can see that the liters cancel out, and then times the molar mass. Again, if you're watching this video and you think this is exactly the gold standard, I have to do everything on the AP Chemistry exam with showing all of these units and conversion factors, no. You can be a little bit sloppy or lazy and still get credit for showing your work. I'm just trying to remind you that when you skip the units, you increase the chances of making a careless error. So anyway, that is the correct answer, 1.99 grams. This was a chromatography experiment. So let's see what the next part of this question is. So as you can see, this is a procedure question in which some steps of the procedure are listed. So we have step 1, step 3, and step 5 that are already printed in the table, and we have to fill in the missing steps to complete the procedure. So how do you prepare 100 milliliters of a 0.340 molar sodium chloride solution? And we have to use the materials from the choices given. Now I see solid sodium chloride, a balance, a pipette, distilled water. I see a volumetric flask, beakers, weighing paper, a scoop, graduated cylinder, chromatography paper. Look at what this student did. I think they were operating under the assumption that they had to use each piece of laboratory equipment in their procedure. So they mentioned a beaker, a graduated cylinder, a volumetric flask, a pipette. But it says clearly not all materials in the list may be needed. So let's go ahead and look at the volumetric flask. Looks like they fill the volumetric flask with distilled water to the calibration mark. Well, that looks good. Remember that if you are preparing a solution starting with a solid, make sure to swirl the mixture to dissolve the solid before you top off the volume to the calibration mark. If you instead top off the volume to the calibration mark and then try to dissolve the solid, that is incorrect. So make sure it's all dissolved and homogeneous before you top off the final volume. Now, can you see what they did wrong? Use weighing paper and scoop to measure the correct mass of solid sodium chloride was already given to you. I think there's a step that you skipped. The student did not mention that the solid sodium chloride should be added to the volumetric flask. They simply skipped that part and talked about the water. So again, before you move on to the next question, I would say if you're on the AP Chemistry free response section and you've just written something down, whether that's a step in a laboratory procedure or a justification or a calculation, before you move on to the next question, just read what you have written. One more time, just quickly read over what you wrote and you might catch, ooh, I forgot to add that particular unit, or I forgot to add that step in the procedure, or I didn't mention what they were asking me in terms of either agree or disagree, or a justification involving some important term or vocabulary. So again, just second guess yourself a little bit before you skip to the next question and realize, I think I forgot to mention an important detail. So here, the student was so focused on adding the water to the volumetric flask, they forgot to mention the part about adding the solid to that same flask. All right, this is the correct answer. After weighing out the solid, combine the solid and some distilled water into the volumetric flask. Again, make sure it all dissolves before you then top off the final volume with the water to the calibration mark, bringing the grand total to 100 mils. Again, be careful you don't add all 100 milliliters at once. That would be another example of a mistake. So we're not adding 100 milliliters of water. We're adding some water, make sure it all dissolves, and then top it off so that the final volume of the entire solution is 100 milliliters or whatever that particular total volume happens to be for your solution preparation. All right, we're still doing this chromatography experiment. Now, in this particular chromatography experiment, we have compound X and compound Y, and it was done over a 30-minute period. And so what we have to do is change it from 30 minutes to 15 minutes. Here's what the student said. Well, if we're using 15 minutes instead of 30 minutes to run the chromatography experiment, they said the solvent has less time to move up the paper. That's true. Compound X and Y would move a shorter distance as compared to trial 1. Also true, but they didn't actually answer the question that was being asked. It said, predict the effect, if any, that this would have on the separation distance between compounds X and Y. Now, to say that compounds X and Y move a shorter distance up the paper, that's not the separation between them. So this is the correct answer. So their mistake was that they didn't say anything about the separation distance between compounds X and Y. So the correct answer is it, as in the separation distance between compounds X and Y, would decrease. The solvent front would not travel as far in the second experiment. So again, not just talking about the compounds' movement, but their separation. That was the important detail that we were looking for in this question. All right, well, this is the chromatography experiment. That was the end of it. Now we're looking at intermolecular forces in this question from 2023. So we have to list all of the types of intermolecular forces. London dispersion forces, yes. Polar substances, therefore dipole-dipole forces, I would say yes. And looks like one of them has the ability to experience hydrogen bonding attractions. Not both, just one. This is what the student said. Well, they said London dispersion forces for both. That looks good. They said hydrogen bonding for the HF. I think they skipped one of the intermolecular forces. So hopefully you can see that they did not mention dipole-dipole attractions. So if hydrogen fluoride as a liquid experiences all three of these, London dispersion forces, dipole-dipole attractions, and hydrogen bonding, then you should list all three. For the HBr, that would be a combination of London dispersion forces and dipole-dipole attractions. So the correct setup you can see at the top of this slide would be LDFs, and you can definitely use that abbreviation on the AP Chemistry exam. The readers know what LDFs mean. We have dipole-dipole forces for both, we have LDFs for both, and we have hydrogen bonding for the HF. Moving on to the next part. This is called enthalpy of vaporization. So what does that mean? Well, enthalpy is the change in energy or heat, and the vaporization is going from a liquid to a gas. So what we have to do is explain, using the types and relative strengths of intermolecular forces, why the enthalpy of vaporization for HF is greater than that of HBr. So this is analogous to talking about boiling points. So let's see if the student did a good job with their answer. All right, this is what they said. Since HF has stronger intermolecular forces, it takes more heat to break the attractions between the HF molecules. Well, I would agree that they talked about the relative strengths, but they didn't mention any specific forces by name, so this is an incomplete answer. The mistake is that they didn't identify specifically the hydrogen bonding as the attractive force that is responsible for the difference in the enthalpy of vaporization for these two substances. So stronger intermolecular forces is vague. Hydrogen bonding is present in a sample of HF as opposed to HBr, and therefore that would be what we're looking for. So here is the official scoring guidelines for this question from the 2023 AP Chemistry exam. You can see that we have LDFs and dipole-dipole attractions for both, hydrogen bonding for the HF, and we have that the enthalpy of vaporization for HF is greater than that of HBr because the forces are stronger in HF due to hydrogen bonding attractions present in HF and not present in HBr. So more energy is required to separate the molecules. So that was our last free response question for Unit 3. Now we're going to take a look at some free response questions for Unit 4. So our next question, which appeared on the 2022 AP Chemistry exam, we are given a balanced chemical equation. I see CH3OH on the left, and on the right I see CO and hydrogen, H2. It says, are the hydrogen atoms oxidized or are they reduced in the forward reaction? Justify your answer in terms of oxidation numbers. And this is what the student said. Hydrogen atoms are reduced because the oxidation numbers are decreasing. Now, that's actually not enough to earn the point. It is true that the oxidation numbers would be decreasing in this example, but the mistake is that the answer is too vague. You need to say what the oxidation number is for hydrogen on both the left side and the right side of the equation. So what are they decreasing from? Is it from 7 to 2 or is it from 3 to 1? And so that's not specific to say that they are decreasing. All right, here's another student answer. Let's see how they did. Hydrogen atoms are reduced because they change from an oxidation number of +4 to 0. Now, I see this from time to time in my own classroom where there are 4 hydrogen atoms in that chemical formula, CH3OH, and so what students do is they add them all up. So the mistake here is that the oxidation number should be assigned to an individual atom in a formula. So the oxidation number of hydrogen in that compound on the left is actually +1. It just so happens to be that there are 4 atoms of hydrogen in that formula, but the oxidation number is not +4, it's +1. That's how we do it. So this would be incorrect if they said it's changing from +4 to 0. Now, this is the correct answer. Are they oxidized or reduced? Well, hydrogen atoms are reduced because they change from an oxidation number of +1 to 0. All right, let's move on to our next question. In this one, we have to write the balanced net ionic equation for the reaction that occurs between H2NNH2, which is known as hydrazine, and then we have HCOOH, which is known as methanoic acid. Now, this question, which was from the 2021 AP Chemistry exam, involves a weak acid and a weak base. And so if you're wondering, how do I know that that's a weak acid and a weak base? Look at those Ka and Kb values. They're rather small. If it was a strong acid and it was on your list of 6 strong acids, the Ka for a strong acid is most likely 1,000 or 1,000,000 or a big number. So this is definitely a weak acid reacting with a weak base based on the small value of Ka and Kb. So all I've done is I've written those chemical formulas on the left. Now, what do I have to show on the other side of the equation? Well, that would be the product of an acid-base reaction. With acid-base reactions, we're looking for proton transfer. So an H+ ion is going to be lost by the acid and gained by the base. So the HCOOH loses H+, and so I will show on the other side of the equation the HCOO- ion. So again, don't forget to include the charges on the ions. And then the other molecule, the weak base, is going to gain H+, and it's going to be right there on that nitrogen, so you can see that would be H2NNH3+. Now, do I have to include the phases of matter? No. I do not have to include states or phases of matter to earn credit, but the equation should be balanced in terms of both atoms and charge, and if there is a chemical formula that's incorrect, either because of a subscript or a charge, well then that would be why you would lose the point for a equation that you're writing. So don't worry about the phases of matter, but make sure it's balanced in terms of both atoms and charge, and make sure that all of your chemical formulas are written correctly. All right, let's go ahead and move on to the next question. In this next question, we have to identify the species that was reduced. So similar to what we looked at earlier with respect to the hydrogen that was reduced, here we have to identify the species that was reduced in this reaction. I'm going to start with hydrogen. It's +1 on the left, and I see water on the right. It's still +1, so the hydrogen is not changing its oxidation numbers. Oxygen, I don't see anything strange like hydrogen peroxide or H2O2. I don't see any exceptions, so oxygen is -2 on both sides of the equation. So what it comes down to is it manganese, Mn, or is it carbon? What's changing in a particular way in this oxidation reduction or redox reaction? Well, I see carbon is +3 on the left. And if you're not sure how I figured that out, oxygen is -2, and there are 4 of them, so that's -8. Ignoring the coefficient, which is not part of my calculations, there's 2 hydrogens that would be +2 collectively for the 2 hydrogens. So if I have -8 for the 4 oxygens and +2 for the 2 hydrogens, that makes the 2 carbons collectively +6, so each carbon is +3 in terms of its oxidation number. Now on the other side, it's a little easier. It's CO2. That would be -2 for oxygen, and you have 2 of them, so the carbon would be +4 in that compound. Now, what happened is that carbon actually went up from +3 to +4, so that's not reduction, that's oxidation. What I know right now is that hydrogen didn't change, oxygen didn't change, and carbon was actually oxidized from +3 to +4. So let's go ahead and answer the question. Identify the species that was reduced in the titration reaction. So I'm going to say something about manganese. Let's see what this student did wrong here. They have MnO4-, which is a polyatomic ion on the left side of the equation, and they say it's changing from -1. And on the other side of the equation, we have Mn2+. Well, I would agree that the manganese on the right is +2, but the student made the mistake of writing the overall charge on the polyatomic ion, which is not actually the oxidation number of the manganese. So manganese is actually +7 in this permanganate ion. So MnO4 has an overall charge of -1. There's 4 oxygens and they're each -2, but that manganese should be +7. So here is the correct answer. The species that is reduced in this equation would be manganese from +7 to +2. All right, our next example involving chemical reactions in Unit 4 is that we have to write a balanced net ionic equation for the given reaction. Now, as you're looking at these 3 reactants on the left, they're all aqueous ionic compounds. And then I see 3 products on the right, 2 of them are aqueous ionic compounds. So here's some guidelines. Do I split up the chemical formula into separate ions, or do I leave it unchanged exactly as written? If it's an aqueous ionic compound, split it up. And as far as aqueous ionic compounds are concerned, sometimes they will tell you, it could be calcium chloride or magnesium sulfate. If they say it's aqueous and you know it's ionic, split it up. The other soluble snap ions that are listed there, those aren't the only substances that could be soluble. So it's possible that they'll tell you that calcium chloride is soluble and you would split it up. And also split up the 6 strong acids. So those 6 strong acids would be split up into separate ions. Now, what do you leave together exactly as written and unchanged? Well, that would be gases, so like CO2 or hydrogen, for example. Liquids, so maybe H2O or some alcohol. Solids, obviously, don't split any of those up. You wouldn't split up something like sugar, where it's sucrose or glucose. It is not an ionic substance, so it might dissolve in water, but it doesn't break up into ions. And then if we split up a strong acid, we do not split up a weak acid. Like I showed you in that earlier question with the weak acid and the weak base, I did not split them up. I left them as one formula. So these guidelines, as you're seeing on this slide, might help you when you're writing a net ionic equation. Okay, so back to the question. Na2S2O3, that consists of sodium ions, and then the S2O3 is a polyatomic ion with a charge of -2. I'm going to split it up into 2 sodium ions and 1 thiosulfate ion, which is S2O3 2-. I see the next aqueous ionic compound. I will also split that up. That would be 4 sodium ions and 4 hypochlorite ions. That would be OCl-. So there's 4 of each. And then I have 2 in front of the NaOH. I'm going to have 2 sodium ions and 2 hydroxide ions. What about the other side of the equation? Sodium sulfate, I will split that up, but there's actually 4 sodiums and there's 2 sulfates. So 4 sodiums and 2 sulfates, split it up. 4 sodiums and 4 chlorides in the next example. And then the only substance I did not split up was something molecular, which is water. So water I would just leave as is. Now, if this was your final answer, you would get this incorrect on the AP Chemistry exam because we have not crossed off our sodium ions, our spectator ions, on both sides of the equation. So if I'm counting correctly, I see 8 sodiums on the left and I see 8 sodiums on the right that appear in identical forms. I'm going to cross them off. this is my final answer. Now, is it balanced in terms of atoms? Yes. I see 2 sulfurs on the left, 2 sulfurs on the right. I see a total of 9 oxygen atoms on the left, and I see 9 oxygen atoms on the right, if I counted correctly. I see 4 chlorines on the left and 4 chlorines on the right, and I see 2 hydrogens on the left and 2 hydrogens on the right. So it's definitely balanced in terms of atoms. What about the charge? On the left, I see -2, -4, -2. That's -8 on the left. And I also see -8 on the right. So it is balanced in terms of both atoms and charge. Let's move on to our next question in Unit 4. This has to do with particulate representation of a reaction. So I'm going to count the product mixture because I don't have a reactant mixture. We have to write the particle level representation of the reactant mixture. So it's got 2 NO at the top of this slide, that's the reactants, plus O2 to produce 2 NO2. Well, I just counted 4 NO2 molecules. So if I look at that balanced equation, if I'm producing 4 NO2 molecules, I think I would need 4 molecules of NO, and I would need 2 molecules of O2. So I'll start with that. Now, if I stopped right here, I would not get credit for my answer because I have to keep going. There's actually 4 unreacted extra leftover molecules of NO. That's the reactant that's left over at the end. So if I don't put those 4 molecules of NO in the box on the left, I would violate the law of conservation of matter. So keep going. The reactant mixture is incomplete. You still need to add those 4 extra or leftover molecules of NO. So I'm going to do that. Now I have the proper number of molecules of each reactant in the box on the left. So this answer is now complete. Okay, well now our next free response question that we're going to take a look at is for Unit 5, Kinetics. So let's start with this question from the 2025 AP Chemistry exam. It talks about something known as dihydroascorbic acid, and it says it can be produced by reacting ascorbic acid with the triiodide ion. Now, we are given information with initial concentration of each reactant, initial rate, and this is what it says. The rate law for the reaction is rate equals rate constant K times concentration of ascorbic acid times concentration of the triiodide ion. Explain how the data in the table support the conclusion that the reaction is first order with respect to the ascorbic acid. Now, earlier in this video lesson, I've shown you examples where the student didn't quite earn the point because their answer was too vague or they left something out. Here's another example. The student said, the reaction is first order with respect to ascorbic acid because when the concentration of ascorbic acid is doubled, the initial rate is also doubled. Now, did they mention anything from the data table or just simply memorize that double the concentration, double the rate? So that's what makes this vague. So the mistake is that they're simply giving us a general statement about double the concentration, double the rate, but the student did not mention the following information. Which trials are being compared? And was the concentration of the triiodide ion, which is the other reactant in this reaction, was that held constant while the value of the concentration of the ascorbic acid was doubled? So hopefully you can see why that response of simply concentration of that chemical was doubled and the rate was doubled is too vague and not very specific, referring to the data from the table. So here is the official scoring guidelines answer, and you can see I'm comparing trial 1 and trial 3. Now, in trial 1, the initial concentration of ascorbic acid is 0.45. In trial 3, the initial concentration of the ascorbic acid is actually 0.9. So yes, it doubled. And then the initial concentration of the triiodide ion remained constant at 1.2. So you can say this in words. You can also show us a calculation to earn credit. So there's a calculation set up that proves that the order with respect to the ascorbic acid is 1, so it's first order. And then in words, comparing trials 1 and 3, so be specific, the rate doubles when the concentration of ascorbic acid is doubled and the triiodide ion concentration is constant, indicating that the process is first order with respect to ascorbic acid. So be more complete and use specific information from a data table if you are given a data table. Let's go ahead and take a look at our next free response question. This question asks us to calculate the value of the rate constant K. Now, we already know the rate law. We know that the rate is equal to the rate constant K times concentration of ascorbic acid times concentration of triiodide. So I'm going to choose trial 1. So I've got my rate law. The initial rate in trial 1 is 2.457 times 10 to the negative 4, and my units are molarity per second. I don't know the value of the rate constant K, but I know that the concentration of ascorbic acid in trial 1 is 0.450 molar, and the concentration of the triiodide ion in trial 1 is 1.200 molar. So it's a good setup. I'm going to go ahead and calculate the value of K. So I just did a little bit of rearranging of the equation. I solved for K, and this is what I wrote down. Now, what did that student do wrong? Well, first of all, 4.55 is actually not the correct answer. They left off the times 10 to the something power. And there's no units. So there's actually two mistakes with this answer. The numerical value is actually 4.55 times 10 to the negative 4. So that makes the number incorrect, but there are no units. Let's suppose that the student wrote this. Looks like they have the right numerical value, but look at those units. Is it molarity per second for the rate constant? Well, I see molarity squared in the setup on the bottom, and I see molarity per second on the top. So the correct units are actually molarity to the negative 1, or reciprocal of molarity, and seconds to the negative 1. So there is the correct numerical value, and there are the correct units. So again, on the rate constant, pay close attention to the setup. I've already talked about units a bunch of times already. Here's another example of why if you don't include units in the setup, it makes it very challenging to figure out what the proper units are for the rate constant. All right, let's go ahead and take a look at our next kinetics question. Here we have two graphs, one of which is a straight line. And so we are given two graphs, and it says, based on these data, the scientist makes the claim that the rate law for the reaction is rate equals rate constant times concentration of NO2 to the second power. In other words, we are given a second order rate law. And the question asks, explain how the graphs indicate that the reaction is second order with respect to NO2. Here is another example of a student answer that is too vague and not specific. This is what they said. Well, the graph on the right is linear. No, that would not be enough to earn the point. The graph on the right is linear. Well, what are you talking about? Why is it second order? Hopefully you can see that the mistake is that it does not show the AP readers that you understand the characteristics of that particular graph on the right. The label on the y-axis is 1 over concentration. The label on the x-axis is time in seconds. So to actually earn the point, this is what you should say. The plot of 1 over the concentration versus time is linear, and that indicates that the reaction is second order with respect to NO2. So again, be specific to the actual information you're given, and the graph on the right is linear was not specific enough. All right, the next question on kinetics we're going to take a look at involves stoichiometry. We have a reaction in which 2 NO2 decompose to produce 2 NO plus O2. And it says, at a certain point in the reaction, the rate of disappearance of NO2 is determined to be 6.52 times 10 to the negative 7 molarity per second. And the question asks, determine the rate of appearance. So not disappearance, which is the NO2 reactant, the rate of appearance in molarity per second of oxygen. Now, I think we probably have to use the coefficients at some point here to answer this question. This is what the student said. Now, is any part of that answer correct? Well, considering that there's a coefficient of 1 for oxygen and there's a coefficient of 2 for the NO2, I would say that oxygen is being produced at a rate that is half as much as the disappearance of NO2. Well, that part is correct. However, why does the student not earn the point? They didn't show any work. So please remember on the AP Chemistry exam, if you can do something simple like divide by 2 on your calculator, well, that's great. But you have to show the AP readers what you did. Your work needs to be on your answer booklet and not stored in your calculator. So this student did not earn credit, even though they had the correct answer, because they didn't show any work. That would be how you would set it up. At least something involving dividing by 2, but not just simply the correct answer without any work shown. So just reminder to obviously be specific with your words, but be specific with how you show the setup for your calculation. No work, no credit on the free response section. Now, our next free response question will fall under Unit 6, which is thermochemistry. So the next free response question will actually fall under topic 6.5, energy of phase changes. Let's take a look. This question was from the 2025 AP Chemistry exam, and we're talking about melting point in the data table, boiling point, enthalpy of vaporization. So it sounds like phase changes are going to be involved in this question. Now here's the details. We have a melting point, a boiling point, and enthalpy of vaporization for 2 different substances. But it says the scientist analyzes the mixture after it is cooled and determines that 8.59 grams of this liquid CH3OH is present. We have to do a calculation. Calculate the amount of thermal energy in kilojoules that was removed to condense the 8.59 gram sample of this substance at its boiling point. So enthalpy of vaporization can either be absorbing heat, changing from a liquid to a gas, or releasing heat as it changes from a gas to a liquid. So this was a condensation. Now, why am I writing Q equals MC delta T? Well, I'm here to show you what a student might do to get an incorrect answer on the free response question. You can kind of think about this and say, am I just going to pick a random equation and just kind of hope for the best? Well, here's what the student did. They wrote down Q equals MC delta T, and then they were encouraged by the fact that the M represents the mass. Oh, it says 8.59 grams. Okay, I'll just go ahead and put in 8.59. Now the student has a dilemma. And the dilemma is there is no specific heat capacity listed in this table. So what they do is they think, well, enthalpy of vaporization, that kind of sounds sort of like specific heat capacity, which, by the way, it is not. And then they look at the melting point and the boiling point and they say, well, those are 2 different temperatures. I think I'll just subtract those 2 numbers and there's my delta T. Okay, so is this the correct setup to answer this question? Absolutely not. But it's a very common thing that when you get frustrated and you don't know what to do, you simply grab an equation and you kind of start plugging in numbers. But let's go ahead and consider that specific heat capacity, which is typically in units of joules per gram degree Celsius, that is not the same thing as the enthalpy of vaporization, which has units of kilojoules per mole. So what I'm going to do now is I'm going to write 37.6 kilojoules for every 1 mole of this substance. Now, considering that I was given grams and I have access to a periodic table, perhaps I could convert 8.59 grams into moles. Now, I could look at the periodic table and add up the atomic masses of carbon and hydrogen and oxygen, but they actually gave me the molar mass in the question itself. So the molar mass is 32.04 grams per mole. I would go from grams to moles using the molar mass, and now I will go from moles to kilojoules. There's no delta T. There's no specific heat capacity. We are not using Q equals mc delta T. We are simply converting grams to moles and then moles to kilojoules. So the correct answer is 10.1 kilojoules of thermal energy, the amount of thermal energy that was removed during the condensation of 8.59 grams of this substance. Now, just a brief comment about endothermic and exothermic in this situation. Technically, if you are going from a liquid to a gas, that would be an endothermic process. And in this case, we're actually going from a gas to a liquid because it says condense. So what you can see here is that there's a negative sign for that enthalpy of vaporization. But they didn't want the change. They just wanted the amount of energy. So the sign was actually not necessary to earn credit. And most likely the AP readers, if they saw negative 10.1 kilojoules, then they would ignore that sign. This wasn't about the sign. It was about the magnitude of heat that was released during the condensation. If it was a delta H, I would have to pay more close attention to my final answer being positive or negative, but this is a Q, or amount of heat, that involves a magnitude. All right, let's go ahead and take a look at our next question, which appeared on the 2024 AP Chemistry exam. Now, we have a reaction involving solutions that are being combined together. So the student combines 100 milliliters of a 0.500 molar solution of something known as lactic acid, and then they mix that with 100 milliliters of a 0.500 molar solution of sodium hydroxide. And this takes place in a calorimeter. This might be a good time to use Q equals mc delta T. I can definitely see solutions being combined in a calorimeter, and we have an initial temperature of 20 degrees Celsius, and we have a final temperature of 23.2 degrees Celsius. So let's try the Q equals mc delta T to calculate the quantity of heat produced in this calorimetry experiment. Now, the mass of the solution would be 100 milliliters of each, so that's 200 milliliters. Of course, volume is not the same as mass, but they say assume that the density of each solution is 1 gram per milliliter. So if I have 200 milliliters of total volume when I combine these solutions together, then with a density of 1 gram per milliliter, 200 milliliters is also 200 grams. So I have 200 grams of solution. Now, with the specific heat capacity, is that given to us in the problem? Yes, its specific heat capacity is 4.2 joules per gram degrees Celsius. So that is not enthalpy of vaporization. That is definitely the specific heat capacity of the combined solution. So what about the delta T? Well, it says the final temperature of the resulting combined solution is 23.2. And the student who set this up was so close to getting the correct setup, but they put the wrong value in for delta T. So what they did wrong is, instead of using the change in temperature, they used the final temperature as their delta T, which is incorrect. So if I start with 20 degrees Celsius for each solution before they're combined, and the final temperature of the resulting combined solution is 23.2, that makes 3.2 the delta T. So I got 2,688 on my calculator when I multiplied 200 times 4.2 times 3.2. So 2,688 actually has 4 significant figures. I think I'm limited by my delta T to 2 significant figures. So I'm going to go ahead and write that my Q, my quantity of heat produced with 2 significant figures, would be 2,700 joules. Now, I have my Q, or my amount of thermal energy. This is not the value for the change in enthalpy, or the delta H, for the reaction. There is a difference between Q and delta H. I don't really care about the sign of Q because it's the quantity the magnitude, the absolute value. So I have 2,700 joules. But what often happens in calorimetry calculations is that you will make a transition from the heat, or the thermal energy, to the delta H, the change in enthalpy for the reaction. That's exactly what we're going to do in the next part of this question. We're going to make a transition from Q to delta H. And so, is this reaction that we just observed classified as endothermic or exothermic, and how can we tell? Remember that the temperature was 20 degrees Celsius before these solutions were combined. And the final temperature of the combined solution is actually warmer. It's 23.2. So this reaction is classified as exothermic. Why? Because the temperature increases as the reaction proceeds. I don't need to worry about the sign of Q, but if I calculate delta H, I definitely need to pay attention to the sign. So if we see a follow-up question that asks us to calculate the value of the change in enthalpy for this reaction, the sign of delta H should be negative because this reaction is exothermic. Well, there it is. The next part of this question is calculate the molar enthalpy in units of kilojoules per mole of reaction. Include the sign in your answer. Now, what I'm doing is I'm multiplying volume times molarity, and that would be 100 milliliters, or 0.1 liters, times 0.5 moles per liter. Now, I'm going to calculate the moles because volume in liters is 0.1, molarity is 0.5 moles per liter, and so 0.1 times 0.5 is 0.05. Now, this is a subtle mistake I'm about to make. So pay close attention to what I am doing now to get from 2,700 joules to my value for the enthalpy of the reaction. I have my moles, but look at what I did in the denominator of that expression. The negative sign is fine. It's an exothermic reaction. The 2,700 joules, I divided by 1,000, so I have 2.7 kilojoules. But look at the denominator of that setup. We have a solution of lactic acid combined with a solution of sodium hydroxide. And what I did, which is incorrect, is I added the moles together. Now, you don't add the moles of each reactant together. So why not? Well, there's 1 mole of lactic acid for every 1 mole of reaction. There's 1 mole of sodium hydroxide for every 1 mole of reaction. If I add the moles together, that is not mole of reaction. That would be twice as many moles as I should. So it's either reactant, but not both of them added together. So my answer on my calculator is incorrect. What I got was negative 27 kilojoules per mole of reaction. Let me go ahead and correct my mistake. It should be negative 54 kilojoules per mole of reaction. So adding the moles together was incorrect. Using the moles of the limiting reactant, in this case I could use either one because they are the same, that gave me negative 2.7, again negative because it's exothermic, 2.7 because I divided by 1,000 to go from joules to kilojoules, and then I picked just one of the reactants, not both. And again, it was a 1-to-1 ratio and I had equal molar quantities, so the correct answer to that question for the delta H is negative 54 kilojoules per mole of reaction. All right, here's our next thermochemistry question. This one is also from the 2024 AP Chemistry exam. And first we have to read the thermometer. Now the thermometer looks like it's between 30 and 40. If I look more closely, it looks like it's between 38 and 39. So I'm going to go ahead and read the thermometer, somewhere between 38 and 39, and this is what I said. I said 38.50. Now, do I just add a 0 because I feel like being extra precise? No, that is incorrect. So the mistake here is that I didn't call it 38, I didn't call it 39, I actually called it 38.50, but since every mark on this thermometer is worth 1 degree, then we can only estimate that final digit to 1 power of 10 smaller than what each line is worth. So the correct temperature measurement should be 38.5. I can't add that 0. That thermometer is not that precise. We can only go to the 10th place on this thermometer. Well, now that I know that the temperature is 38.5, let's do some thermochemistry calculations. We have a hot metal, and the hot metal is added to a cooler sample of water. And so we have a metal that was at 100 degrees Celsius. Now it is at 38.5 degrees Celsius. We had some water, which was at 25 degrees Celsius. Now it is at 38.5 degrees Celsius. So someone lost heat and someone gained heat in this transfer. So the metal lost heat. The water gained heat. So the Q equals mc delta T for the metal is equal to the mc delta T for the water. So I've got 98.1 grams of metal. I'm looking at the data in the table. The specific heat capacity of the metal is, I don't know. The delta T for the metal would be the difference between the initial and the final. So that would be 100. Now we're not doing 100 minus 25. Those are two different initial temperatures. We're doing 100 minus 38.5. And for some of you watching this video, you might remember that sometimes in my videos, I do not pay attention to the sign of Q, but I have a reason for that. I care about the magnitude of heat. I do not care about the sign of heat. So when I focus on my thermal energy calculations, if my delta T does not look like your delta T in terms of T final minus T initial, that's because I'm only caring about the magnitude or the absolute value. So I wrote 100 minus 38.5. If you choose to write 38.5 minus 100, we get the same absolute value for that. Now with respect to the other side of the equation, we have the mass of water, which is 52 grams. We don't have the specific heat capacity of water. Do we need to memorize this? Okay, let me move on to the next part. What's the delta T for the water? I would say 38.5 minus 25, which is 13.5. Now you might be a little bit confused because we have mc delta T for the metal, we have mc delta T for the water, and I say, do we need to memorize the specific heat capacity of the water? Let me read the question a little more carefully. It says, assuming that the metal transfers, they just gave us the amount of heat in joules, so I don't need to know the specific heat capacity of water to do this calculation. If I read carefully, it says 2,940 joules of thermal energy was transferred from the metal to the water. So I'm going to replace the right side of my equation with 2,940. I'm just paying attention to the details of the information I was given. I will now solve for C, which is the specific heat capacity of the metal. And when I do that math, I get 0.487. Now earlier I was talking about sign and T final minus T initial and losing heat and so forth. So what I wrote down on my scratch paper in my answer booklet is a number for the value of the specific heat capacity of the metal of negative 0.487. Now, would I earn credit for my answer if I list my specific heat capacity of my metal as a negative number? And the answer is no. Unfortunately, I got that close, but because I put a negative sign on my specific heat capacity, that makes this incorrect. The specific heat capacity of a substance cannot be a negative number. So what is the correct answer to this question? 0.487 joules per gram degree Celsius, but don't put that negative sign in your answer for a specific heat capacity. Let's go ahead and take a look at our next thermochemistry question. This one is actually an extension of the previous experiment. So what we're doing in this next part of the question is we're considering that the first experiment was a particular metal, and the second experiment is now aluminum. Same mass, same amount of thermal energy transferred, but it says that aluminum has a specific heat capacity of 0.897. And what we have to do is the following. Explain how the magnitude of the temperature change of the aluminum compares with the magnitude of the temperature change of the metal in the original experiment. Now, what this is about is, do you understand the relationship between the delta T and the specific heat capacity of the metal? So I'm going to show you an incorrect answer. This is what the student said. They said that the temperature change in the second experiment should be higher because the specific heat capacity of aluminum is higher. Now, they thought that it was a direct relationship between specific heat and delta T, but in fact, it turns out that the relationship between the delta T and the specific heat is an inverse relationship. So because of that inverse relationship, what we have is a larger value for the aluminum's specific heat. Therefore, our prediction is a smaller delta T. Here are the official scoring guidelines. So the scoring guidelines say that the value of the change in temperature for the experiment involving aluminum, the delta T, will be smaller because aluminum has a greater specific heat capacity. So connecting the inverse relationship of those two variables and making the correct prediction that the delta T would be smaller. You can also explain this mathematically. So there's the 2,940 joules of energy that was transferred. We have the mass of the aluminum, we have the specific heat of the aluminum, and we discovered that 33.4 degrees Celsius is a smaller change in temperature as compared with 61.5 degrees Celsius. So either way, in words or in mathematical calculations and setup, you can say that the delta T for the aluminum experiment will be less than the delta T for that first experiment. All right, our next free response question will be for Unit 7, Equilibrium. Now, the first question that I would like to show you, this appeared on the 2025 AP Chemistry exam, and what we have to do is write the expression for the solubility product constant, or KSP, for magnesium hydroxide. And the equation for the dissolution of magnesium hydroxide is given in the question. Oh my goodness, there were so many variations of incorrect responses to this question. So take a look and then also make sure that you don't do this on the AP Chemistry exam when you have to write an equilibrium constant expression. So mistake number 1, including the term for the solid in the denominator of that expression. Next one, multiplying the hydroxide concentration by 2, so there's a 2 inside the brackets. That makes that expression incorrect. Another mistake is to use parentheses in the KSP expression instead of using square brackets to indicate concentration. So square brackets, not parentheses. And then the next two mistakes are either omitting the charges on the ions, so magnesium is +2 and hydroxide is -1, or omitting that exponent in the KSP expression, so the hydroxide concentration should be squared. So what you're looking at are many different ways in which students can write an incorrect equilibrium constant expression. So pay attention to the close details so that you can earn the point for an equilibrium constant expression response on the AP Chemistry exam. Now, that is the correct version of KSP. Let's go ahead and take a look at our next free response question. Now, for this question, which also was on the 2025 AP Chemistry exam, what we have to do is consider the following information from the particle diagram. It says, if each particle in the diagram represents a partial pressure of 1 atmosphere, what is the value of the Kp for this equilibrium mixture? So I'm going to write products over reactants, and because it's Kp, I'm going to use the partial pressure of PCl5 on top, and then the partial pressure of PCl3, and the partial pressure of Cl2 on the bottom. Now, I wasn't graded on this question as to the quality of my Kp, but if they say write the Kp, then this is a good representation of partial pressure and its products over reactants. Since all the coefficients were 1, there were no exponents to worry about. But what they were looking for is plugging in these numbers. Now, if I count the particles, in the diagram, I see 4 particles of PCl5. I see 6 particles of Cl2. And I see 2 particles of PCl3. But look at what the student did incorrectly. They assumed incorrectly that it said each particle in the diagram represents a partial pressure of 1 atmosphere. So it's likely that they misinterpreted that information and said, oh, each substance has a partial pressure of 1 atmosphere, which is incorrect. So they just put 1 atmosphere for the partial pressures of all 3, and they didn't actually count the particles themselves. So if I'm counting correctly, I see 4 particles of PCl5, 2 particles of PCl3, and 6 particles of Cl2. Now that's 4 divided by the product of 2 times 6. That's 4 over 12, or 1/3, and they would accept either the fraction 1/3 or the decimal version of 0.333. Now, the next part of this question is not a calculation, but rather your understanding of Le Chatelier's principle as it relates to temperature changes. So we have a Le Chatelier's principle situation. It says, does the value of the equilibrium constant Kp increase, decrease, or remain the same when the temperature is increased to 596 Kelvin? Now, temperature does affect the value of the equilibrium constant, so therefore this is going to be either increase or decrease. If you change the temperature, you definitely change the value of K. But is it increase or decrease? We have to consider the delta H, which happens to be negative. Here's what the student said. And again, this is going to be incorrect, but here's what they said. If the temperature increases, the value of Kp would decrease. And their justification is because delta H is negative, so the reaction is exothermic. Now, it is true that delta H is negative. It is true that the reaction is exothermic, and I'm fairly certain that as temperature goes up, the value of Kp will decrease. But unfortunately, the student didn't really explain the details. So if you're not sure what they did wrong, if you are talking about a shift either to the left or to the right, then that would be very important to mention. And the student did not indicate the following. Exothermic reactions will favor the reactants, as in there's a net conversion from products to reactants when the temperature is increased. So with questions involving Le Chatelier's principle and temperature in this case, clearly state the direction in which the reaction system will proceed as a result of the change that occurred. This is not a Q versus K situation. This is a temperature went up, the reaction is exothermic, and there will be a net conversion from right to left, causing the value of K to decrease. So here's the official scoring guidelines answer. So, will the value of Kp increase, decrease, or remain the same when the temperature is increased? They said decrease, which is correct. The negative value of this delta H indicates that the reaction is exothermic, so that's good. Because exothermic reactions favor reactant formation at higher temperature, the value of Kp decreases. So there's a clear indication of the direction in which the reaction would proceed. But that student that said, well, delta H is negative, it's exothermic, and Kp would decrease, they never actually talked about the direction in which this reaction would proceed. So again, there's the correct answer. Exothermic reactions favor reactant formation at higher temperature, causing the value of Kp to decrease. Now, here is our next equilibrium question, and now we have to write a Kc. And we have to write a Kc, not a Ksp, but a Kc. And again, there were so many variations of incorrect responses, so it's going to be brackets, products over reactants. I don't see any charges to worry about, but I do see a potential exponent in the numerator. So using parentheses instead of square brackets was incorrect. It was supposed to be a Kc, so writing the Kp would be incorrect. The next one was flipped upside down, so writing the reciprocal was incorrect. Again, these are all incorrect responses. omitting that exponent in the numerator. The coefficient of HI is 2. And this one is a little bit subtle, but watch out for that. Yes, the reactants are separated by a plus sign in the balanced equation, but do not put a plus sign between two components of your equilibrium, because that is multiply, not add. So by putting that plus sign, you did not earn the point, because that's the wrong mathematical operation. And again, like I mentioned with the KSP, do not put a 2 inside the brackets as an extra little coefficient. That would also be incorrect. So all of these are examples of answers that did not earn the point for the KC expression. There's the correct answer that they were looking for. Concentration of HI squared divided by the product of the concentration of hydrogen and the concentration of iodine. All right, here's the next question. It involves a particle diagram. Now it says that this particle diagram is incomplete. The Q, the reaction quotient, is equal to 0.67, but we don't have HI at all in this diagram. I see 2 particles of iodine, or I2. I see 3 particles of hydrogen, or H2, but there's no HI. So we have to draw the number of HI molecules so that the reaction quotient has that particular value. So the student incorrectly drew 4 molecules. Now, why is that wrong? Well, it doesn't equal the value of the reaction quotient. So why did they do that? Why did they draw 4 molecules? It's possible that the student was thinking about stoichiometry and they thought, well, there's 2 molecules of iodine, perhaps reacting with 2 molecules of hydrogen. So they might have been trying to convert reactants into products, but they didn't consider the value of the reaction quotient. So what's the value of the reaction quotient? Well, the value of the reaction quotient is 0.67 is equal to the concentration of HI squared, which we don't know what that number is yet, divided by the concentration of hydrogen, which is 3 in this case, and then the concentration of iodine, which is 2. So let's go ahead and complete the math. 3 times 2 is 6. So now I have concentration of HI squared divided by 6 is equal to the reaction quotient, which is 0.67. So now I'm going to go ahead and multiply both sides by 6. And when I do that, I get 4. Now, it doesn't mean I'm drawing 4 HI molecules because it's squared. It's concentration of HI squared is equal to 4. So the square root of 4 is 2. And the correct answer to this part is that how many molecules of HI should be drawn? Only 2 molecules of HI should be drawn to complete the mathematical representation of the reaction quotient Q, which is equal to 0.67. Now, there's another part of this which is related to Le Chatelier's principle. How do I know this is related to Le Chatelier's principle? Well, at some point, there was a change that occurred, and that change happened right there where the dash is indicated as time. So it says, what experimental change could have been applied to the system at time t to result in the change in the number of moles of HI shown in the graph? So after the change happened, the number of moles of HI increased, so there was a net conversion from left to right. There was a net conversion from reactants to products as a result of the change. So what sort of change would cause the system to experience a net conversion from left to right? Well, if we add more hydrogen, it would proceed from left to right. If we added more iodine, it would proceed from left to right, and possibly a change in temperature. But would the temperature increase or decrease? Well, we have an exothermic reaction. If the temperature is decreased, an exothermic reaction will experience a shift from left to right. So possible things you could have said that would cause the number of moles of HI to increase would be any of the following. Decreasing the temperature, that would cause a shift from left to right. Adding more of either the reactant, hydrogen or iodine, that would cause a shift from left to right. So that's the answer to that particular question. Now there's one more, and that is what happens after equilibrium is established is we're going to take the mixture and transfer it to a larger container. So we have a system that is at equilibrium, and we take that mixture and we transfer it to a larger container. And we have to determine, will the number of moles of HI increase, decrease, or remain the same? Now this is at constant temperature, but will that number of moles of HI be affected by transferring the mixture into a larger container? So here is an incorrect answer. Now what the student thought was that somehow if you increase the volume, you have to increase the moles to match. What they were thinking is that the concentration of HI has to be held constant, so they thought more moles would have to be the result because now we have more volume. They're trying to somehow go back to that original molarity that we had before the change. And so here's my advice. When it comes to situations involving Le Chatelier's principle, it's always a good idea to make a comparison of Q versus K, and you can't always do that, especially if it's like a temperature change. You can't do that, but here, let's go ahead and consider Q versus K. So what do we know? Well, we had a container whose volume increased. Let's imagine that the volume of the container doubled. Now, why am I saying doubled? I just want to do some simple math. So if you double the volume of the container, you're cutting the concentrations in half. If you double the volume of the container, you're cutting each of the concentrations in half. And now that's my reaction quotient. So I have 1/2 times HI, which is squared. I have 1/2 times H2, 1/2 times I2, and it turns out mathematically, if you increase the volume of the container for this system, Q remains equal to K. So will the number of moles of HI increase? No. Will the number of moles of HI decrease? Also no. They will remain the same because Q remains equal to K. So either of these were accepted as far as the official scoring guidelines. The answer is remain unchanged. So one possible justification is that the number of moles in both the numerator and denominator of Q or K are equal. So changing the volume of the container would not alter the value of Q. And if Q remains equal to K, the number of moles of HI remain the same. Another justification is to indicate that you're decreasing the concentration of the reactants and the products by an equal proportion. And so again, because there are equal moles of gaseous reactants and products in this equation, there will be no shift either to the left or the right, and the number of moles of HI will remain the same. So again, Q versus K, if you can do it, would be a really good strategy on the free response section of the AP Chemistry exam, especially when you have to justify your answer for your prediction. All right, and now our next free response question will be under Unit 8, Acids and Bases. So the first free response question I would like to show you is from the 2025 AP Chemistry exam, and it says calculate the pH of the solution in beaker 2. Now, the solution in beaker 2 has a concentration of 2.8 times 10 to the negative 4 moles per liter. So the student picked up their calculator and took the negative log of that number, and then they stopped. Now, if this were a strong acid, then a pH of 3.553 would be correct. But sodium hydroxide is actually a strong base, so their mistake is that they forgot to do that 14 minus POH to get the pH. So the negative log of the concentration of the hydroxide ion in that beaker is 3.553, and then 14 minus the POH will give us the pH. So the correct answer was not 3.553, but rather 10.447. So when you are solving problems on the free response section of the AP Chemistry exam and you have to work with pH or POH, just be very careful and pay attention to that quantity that you are taking the negative log of on your calculator. If it's an acid, a strong acid, then negative log of that number will be the pH. If it's a strong base, take the negative log of the concentration of the hydroxide ion, and then don't forget to do 14 minus the POH. So this question from the 2025 AP Chemistry exam actually falls under topic 8.11 pH and solubility. And this is what it says. In a separate experiment, the student adds nitric acid, which is a strong acid, to decrease the pH of a saturated solution containing undissolved magnesium hydroxide. And here's the question. Does the amount of the undissolved solid magnesium hydroxide increase, decrease, or remain the same when the strong acid, the nitric acid, is added? Justify your answer. So here's an example of what a student said that did not earn the point. Now, they said that the magnesium hydroxide remains the same because nitric acid does not have any common ions with the magnesium hydroxide. Now, there is something in Unit 7 called the common ion effect, where a solution becomes less soluble if there is a common ion present. But in topic 8.11, pH and solubility, something that is a strong base, such as this magnesium hydroxide, that actually can be affected by a strong acid, it is going to be affected by the presence of acid. So the mistake is that the student didn't recognize that the solubility of a salt that contains hydroxide ions will be affected by the addition of a strong acid. So now here comes another example of, did the student actually justify their answer appropriately? All right, the magnesium hydroxide will decrease is actually correct. The amount of undissolved magnesium hydroxide will decrease, but let's see what they said. They didn't say anything. So the student answered the question but did not justify their answer. So please make sure that you don't just increase, decrease, or whatever, and then stop. Make sure that you justify your answer. You're not going to get a point for simply guessing on increase, decrease, remain the same. So that's why they didn't earn the point. Now, here's what this student said. Since nitric acid is a strong acid, and that's true, it will react. But what they're talking about is they're talking about it reacting with the solid magnesium hydroxide. And they go on to mention that the equilibrium would shift toward the right, and the amount of undissolved magnesium hydroxide will decrease. So the problem is, this is kind of subtle, is that we're talking about Q versus K, and we don't include solids in the equilibrium constant expression or the reaction quotient expression. So to indicate that there's a direct reaction between the strong acid and solid doesn't actually affect the value of Q. So if you're going to have a saturated solution, you need to focus on the acid reacting with the aqueous portion, not the solid portion, but the aqueous ions. So the correct answer is the following. Yes, the amount of undissolved magnesium hydroxide will decrease, but I'm not showing the acid reacting with the solid. I'm showing the acid reacting with the hydroxide ions that are already in solution. Here comes the Q versus K. Acid reacts with hydroxide. Hydroxide concentration decreases, causing Q to become less than KSP. And now there will be a net conversion from left to right. And so as a result, more solid magnesium hydroxide will dissolve. And so it's about the cause being the reaction in the aqueous component, not the reaction with the solid, but with the aqueous hydroxide ions. And then the effect is a net conversion from left to right, and therefore increasing the solubility, decreasing the amount of undissolved solid. All right, let's go ahead and take a look at our next acid-base free response question, and we see a titration curve. Now, in this particular titration curve, sometimes they might ask you about the pKa, sometimes they might ask you to do some sort of molarity calculation. So let's go ahead and take a look at the titration curve. And the question says, calculate the molar concentration of the ascorbic acid solution. Now, there's molarity and there's volume for the acid. There's molarity and volume for the base. I see a 1-to-1 mole ratio between the ascorbic acid and the sodium hydroxide in this reaction. So because I'm looking at molarity and volume of acid and molarity and volume of base with a 1-to-1 mole ratio, for the reaction between the strong base and the ascorbic acid, I can use this particular equation. But still, be on your guard. Be careful that you use the correct molarity with the correct volume. Now, I'm showing you that there's a volume of 16 milliliters on the graph. That would be the volume of the sodium hydroxide. So I have 16 in my equation. I also have 10 in my equation. And if you're wondering, well, where did you get the 16 from? It's from the titration curve, the equivalence point. Where did you get the 10 from? It says 10 milliliters of ascorbic acid was titrated. So the mistake is that I flipped those numbers accidentally, right? So that the student, what they did is they put the 16, which is the volume of the sodium hydroxide, connected to the unknown concentration of the acid, and then they put the 10, which is the volume of the acid solution that was titrated, with the sodium hydroxide. So in the setup for their calculation, they reversed the volumes. Now, there's the correct answer. Molarity of acid times 10 milliliters equals the molarity of the base, the sodium hydroxide, the 0.0550 molar, times 16, which again, that 16 comes from the volume at the equivalence point of the titration. So that is the correct setup and the correct answer. Now, moving on, I mentioned that sometimes they ask you to calculate the pKa, or determine, I should say, the pKa. So there's not really a calculation. It's simply a look at the halfway point. Well, here's the student, and they said that the pKa was 8. 8 is not the pKa. And I'm not really sure what they did wrong by choosing 8. Is it because they looked at the wrong axis? They may have looked at the x-axis and said, I know it's the half equivalence point, but they wrote down the number 8, which was the volume of the titrant and not the pH of the solution. Or they might have actually been looking at the wrong pH. They might have been looking at the pH at the equivalence point instead of the pH at the half equivalence point. Nonetheless, for whatever reason, a pKa of 8 is incorrect. So I think it's approximately 4, perhaps just slightly higher than 4, and they would have accepted a range of values that were reasonable. So I'm going to say that the pKa is 4.1. And now the next part of this question, again, this is from the 2025 AP Chemistry exam, is the following. What is the value of the ratio of A- over HA, basically, the concentration of the ascorbate ion, A-, over the concentration of the ascorbic acid, HA? What is the value of the ratio when the pH is 4.7? So I'm going to go ahead and use the Henderson-Hasselbalch equation. So 4.7 is what they just told me. 4.1 is the pKa that I determined from the half equivalence point pH. I've got 4.7 and 4.1. Now, I know the difference between 4.7 and 4.1 is 0.6. What did the student do wrong? Just a very slight change, and that's actually incorrect. It should be the number 10 raised to the 0.6 power. So the exponent should be positive 0.6, not negative 0.6. So what is the correct answer? Well, 10 raised to the positive 0.6 is actually the number 4. So there's the correct answer. So we did the molar concentration. Again, be careful you don't reverse your volumes. So that was the first part, and that was a molarity of 0.088 molar. Watch out that you get the correct pH at the half equivalence point. And if you're doing something involving the Henderson-Hasselbalch equation, make sure that you use the correct calculation. So that was supposed to be 10 to the positive 0.6, and we got a ratio of 4. Now, here is a new question from the 2025 AP Chemistry exam, but this is a different question. And what we have to do is actually calculate the Kb. So read the question carefully, make sure you answer the question that's being asked, and then double check, do I have all of the numbers in the right locations? Do I have all of the numbers in the right locations? So I put 1.3 times 10 to the negative 5 on the left. I put 2.5 in the denominator of my expression, and I'm solving for x. Oops. The 1.3 times 10 to the negative 5 is not the equilibrium constant. In fact, we are looking to calculate the value of Kb. So what exactly is that 1.3 times 10 to the negative 5? That is the concentration of the hydroxide. So that goes right there. It goes in the numerator of the expression. If I'm solving, it's not going to be x and x in the numerator. It's going to be 1.3 times 10 to the negative 5 for the concentration of the hydroxide ion that I was given. And then what about the other substance in the numerator? Well, it's going to be based on the 1-to-1 mole ratio on the right side of the equation. It's going to be that same number again. So the 2.5 is in the denominator. The 1.3 times 10 to the negative 5 is in the numerator twice because of the 1-to-1 mole ratio. I'm going to square that number. So 1.3 times 10 to the negative 5 squared divided by 2.5, and that is my value of Kb. So the mistake that I made is I put the number in the wrong spot, and I treated this as a different type of problem, as if I knew the K value, which I did not. So there's the correct answer. We calculated the value of Kb, and you might know there's an inverse relationship between Ka and Kb. However, you don't just take the reciprocal. There is an inverse relationship between Ka and Kb, but it is incorrect to simply take the reciprocal of the Kb. So this is an incorrect answer, and the mistake is that there's no Kw in their setup. That is correct. So it's not 1 divided by the Kb, it's actually Kw divided by the Kb. And you can find that equation on the equation sheet. So that is incorrect. This is the correct answer. And so the Kw divided by the Kb is equal to the Ka. Our next acid-base free response question is we have to circle the hydrogen atom that most readily participates in a chemical reaction. And you might know what are called carboxylic acids. But if you don't know what a carboxylic acid looks like, you might circle the wrong hydrogen atom. So the student did not circle the correct hydrogen atom. This should be recognizable to you from topic 8.6, molecular structure of acids and bases. This portion, or this section of the structure of this weak acid molecule should be recognizable to you as a carboxylic acid. So that hydrogen is the one that should have been circled for the carboxylic acid. So just keep that in mind. That's topic 8.6. All right, now we should see another titration curve. Let's go ahead and find the halfway point again to determine the approximate pKa. Now, what the student did incorrectly is they wrote the answer for the pKa like this. Again, we're not exactly sure why they wrote 8 instead of the correct answer, which is going to be approximately 4, maybe around 3.9 or so. So is it possible that they looked at the wrong pH? The pH at the equivalence point, that's incorrect. Or they might have looked at the wrong location on the graph, looking at the x-axis as opposed to the pH at the half equivalence point. So I would say it's approximately 4. Now, 3.9 is what I'm choosing to say, but there was an acceptable range on the AP exam for the 2024 free response question number 1. The pKa was in the range of 3.7 to 4. All right, what's the next part of this question? Well, we have a particle diagram, and we have to draw an X on the titration curve that would match this particular particulate diagram. So I can see in the particulate diagram some acid and conjugate base. I've got 4 molecules of HA, and I've got 2 particles of A minus. Now, if we are before the halfway point, there's more HA than A minus. If we're after the half equivalence point, there's more A minus than HA. And we have to draw an X on the diagram, on the titration curve, to match this diagram. Looks like there's more HA than A minus, so we should be before the half equivalence point, and I put my X right about there. Again, there'd be a range of acceptable values for that. It does say justify your answer, so they accepted somewhere between 3 milliliters and 8 milliliters on the 2024 AP Chemistry exam. So I'm going to justify my answer by saying, well, there are more acid particles present in that mixture than conjugate base. So there's more HA than A minus. There's more of the C3H6O3 than there is of the C3H5O3 minus. So the titration is before the half equivalence point. All right, the next question, the next free response question for Unit 8 involves drawing a new curve. The student repeats the experiment, but uses a solution of sodium hydroxide with twice the concentration as in the previous titration. So we already have the titration curve for trial 1. Now we have to draw a new titration curve when we doubled the concentration of the sodium hydroxide. Don't change the initial pH because we are titrating the same acid. So the initial pH is the same. What's changing is the location of the equivalence point. So on this student's titration curve, they did not earn that point because they moved the initial pH to a different value. So that would be incorrect. So the location of the equivalence point, if we have double the concentration of sodium hydroxide, would be that now the location of the equivalence point should be at 8 milliliters instead of 16 milliliters. So again, on that student's graph, they did not earn that point because the location of their equivalence point did not change. It should have been at 8 milliliters. So there, on the official scoring guidelines, is that the equivalence point should be located at 8 milliliters because we doubled the concentration of the titrant. So we cut the volume of the titrant in half as far as that's concerned. And the initial pH should be the same in both trials. And the general shape of the curve should follow that similar pattern where it begins at the same pH, gradually increases, rises sharply at the equivalence point, and then eventually levels off. So it kind of matches that. So those are the official scoring guidelines for that question that appeared on the 2024 AP Chemistry exam. Our next free response question that we're going to take a look at is from Unit 9, Thermodynamics and Electrochemistry. So the first free response question I would like to show you came from the 2025 AP Chemistry exam, and it involves a change in entropy. It says the entropy change for the reaction, delta S, is negative. Using particle level reasoning, explain why the entropy decreases as the reaction progresses. Now, I can see in this equation 1 mole of solid reacting with 5 moles of gas, producing 1 mole of solid. This is what the student said, and they did not earn the point for their response. They said that the reactants include both a solid and a gas. The only product formed in this reaction is a solid. Solids are more ordered and have less entropy than gases. Thus, the entropy decreases as the reaction progresses. So I'm not sure if you can see what's missing, because that sounded perhaps to you as a pretty decent attempt at describing a change in entropy, but the student's response does not include any particle level reasoning. So common adjectives and phrases that are used in responses involving entropy are dispersal, microstates, number of arrangements, degrees of freedom, configurations, orientations, again referring to the particles. So not just solid, gas, ordered, disordered, but focusing on the arrangements, microstates, dispersal, degrees of freedom. So here is the official scoring guidelines answer for that question from the 2025 AP Chemistry exam. Because gas particles are more dispersed, have more microstates than solids, the entropy decreases as the reactants, which include a gas, convert to the solid product. Again, particles was not something that was included in the student's answer to that question. They only talked about the solid and the gas and compared the entropy. So particle level reasoning, dispersal, microstates, number of arrangements, degrees of freedom, configurations, orientations of the particles. All right, our next free response question is going to relate to delta G. So it's the follow-up to this particular question. So this question says that the enthalpy change, delta H, is also negative. So we have a negative delta S, we have a negative delta H. A student claims that the favorability of the reaction is driven by enthalpy and not driven by entropy. So is the student's claim correct? Justify your answer by using the relationship between delta G, delta H, and delta S. This is what the student said that did not earn the point. Student said, I agree with the student's claim. Again, the student's claim is that the favorability of the reaction is driven by enthalpy and not by entropy. So they say, I agree with the student, both delta S and delta H are negative. Thermodynamic favorability is supported by a negative delta H. Thermodynamic favorability is not supported by a negative delta S. Now, if you're wondering, what exactly is that answer lacking? Well, first of all, do you see anything about delta G in that response? No, I don't see if I've understood that the student's talking about thermodynamic favorability without even mentioning delta G. So this student's response is mostly a restatement of information that had already been given in the question. The student has not demonstrated that they understand the following. If a reaction is thermodynamically favored, what is the sign of delta G? They never said that. And what is the Gibbs free energy equation? And how does the sign of delta H and delta S affect the sign of delta G? So that's what's lacking in this student's response. So talk about delta G, talk about the sign of delta G as it connects to thermodynamic favorability, and then talk about the relationship between delta H and delta G. And again, talk about the relationship between delta S and delta G. So here's the official scoring guidelines answer. Yes, I agree with the student's claim that the favorability is driven by enthalpy and not driven by entropy. So they right off the bat give us the Gibbs free energy equation. So delta G equals delta H minus T delta S. That's a good start. Then they went on to say that the reaction must have a delta G that is negative to be favorable, a very essential component of your answer. Now, because the reaction is exothermic, we have a negative delta H, and enthalpy contributes to favorability. Because the delta S is negative, entropy does not contribute to favorability. I've got some more examples a little bit later in this lesson on the Gibbs free energy equation. So if you're still confused about how exactly you should justify your answer with respect to thermodynamic favorability, stay tuned a little bit later in this lesson and I will talk about delta G, delta H, and delta S a little bit more. But now we're going to take a look at an electrochemistry question. So here we have a diagram of a galvanic cell. This question appeared on the 2025 AP Chemistry exam. I can see a zinc and aluminum electrode, and there's a container of zinc nitrate on the left and aluminum nitrate on the right. So we have a galvanic cell. As the cell operates, it says that the zinc electrode increases in mass. And as the cell operates, the mass of the aluminum electrode decreases in mass. So how does that help me determine whether zinc is a reactant or a product in the solid state? Well, if the zinc electrode is increasing in mass, zinc should be a product. If the aluminum electrode is decreasing in mass, that actually means aluminum solid is a reactant. So we're forming more solid over time. That's why the zinc electrode gets heavier. We're consuming aluminum solid over time. That's why the mass of the aluminum electrode gets lighter. So now I have to write the half reaction for the oxidation that occurs in the anode. Well, this is what the student wrote, and they are incorrect. Is this, what the student just wrote, is that an oxidation reaction? I see zinc changing from +2 to 0, and it's gaining electrons. So that is incorrect because this is a reduction half reaction. All right, well then the student flips it around. Now we have an oxidation half reaction, but it doesn't match the information we were given. If I put zinc solid on the left as a reactant, that's not going to explain why the zinc electrode actually gets heavier. So solid zinc must be formed as a product because they told us that the mass of the zinc electrode increases in mass. So where's my oxidation reaction? It's not going to involve zinc. It's going to involve aluminum. So there's my aluminum changing from a solid to the aqueous ions, and I've got 3 electrons involved in that half reaction. Now, moving on to the next part. Write the balanced net ionic equation for the overall reaction that occurs in the galvanic cell. So my answer to part A, which was the oxidation half reaction, is solid aluminum turning into aqueous aluminum ions plus 3 electrons. Phases of matter are not required, but there is still a mistake. Can you see it? Aluminum plus zinc 2 plus, producing aluminum 3 plus and zinc. Well, the mistake is that this equation is not charge balanced. I have positive 2 on the left, and I have positive 3 on the right. So now I have a balanced equation involving a positive 6 on the left and a positive 6 on the right. So the correct answer to the overall balanced net ionic equation for the reaction that occurs in this galvanic cell is 2 aluminum plus 3 zinc 2 plus ions produces 2 aluminum 3 plus ions plus 3 zinc. Now, the next part is actually kind of a stoichiometry question, not so much a electrochemistry question. It's more about moles and grams and stoichiometry. It says, initially, each electrode has a mass of 50 grams, and the galvanic cell is allowed to run for a period of time, and then eventually it is stopped. But it said which electrode's mass changed the most. Which electrode's mass changed the most? Now, here is an incorrect student response to that question. What they said was, well, the mass of the zinc electrode should change the most, because there's 3 moles of zinc produced for every 2 moles of aluminum that are consumed. And are they comparing the grams? No, they're actually comparing the number of moles. So the student is only comparing the number of moles. They did not include information from the periodic table about molar masses. So moles only is not a satisfactory explanation. So which electrode's mass changed the most? Here are the official scoring guidelines. You can see that 26.98 is the molar mass of aluminum, 65.38 is the molar mass of zinc. So they're using both a grams to moles conversion as well as a moles of one chemical to moles of another conversion. Now, when they do that, they discover that 50 grams of aluminum is transformed into 182 grams of zinc based on the stoichiometry calculations. So therefore, zinc experiences a greater change in mass, assuming that the entire aluminum anode reacts. You could also just simply compare 1 mole of reaction for each of these and discover that the change in mass for zinc is greater. And then at the bottom of this slide, you can see words. Zinc experiences a greater change in mass because 3 moles of zinc are used for every 2 moles of aluminum. And then here's that connection to molar mass. 196 grams of zinc are produced for every 54 grams of aluminum that are consumed. So a variety of ways of earning the point for that question, which is which electrode's mass changed the most. But just talking about moles was not enough. All right, now this one, which is also from that same question from the 2025 AP Chemistry exam, it says that the standard aluminum zinc cell has a value for the cell potential of 0.90 volts, and the scientist needs a galvanic cell that produces a greater voltage. Now I see 1, 2, 3, 4, 5 different half reactions, and if I'm looking for the greatest voltage, I might pick this one, which is gold, and that's 1.50 volts. I might also pick this one, which is beryllium, but of course I have to reverse it because you can't have 2 reductions. So I did 1.5 plus the reversed of the other one, and I got 3.35. I'm feeling pretty proud of myself until I realized I didn't read the question carefully. So what I did was I just tried to find the maximum voltage, but it said specifically if the scientist uses the zinc half cell and one other of the options from the table, what is the maximum voltage that could be generated? So my mistake is that I didn't use zinc at all. One of the half reactions must involve zinc. Now, zinc is negative 0.76. So if I flip it, that would be positive 0.76. But if I do reverse that reaction, I need another one to be combined with it. So I can't reverse both reactions. I have to reverse only one of them. So I'm reversing the zinc makes that an oxidation. So which reduction should I use? I'm going to use the gold. So I have positive 0.76 because I reversed the zinc half reaction. I have to use zinc. I have 1.5. So 1.5 plus 0.76. I got 2.26 volts, and that is, if you check the scoring guidelines for 2025, that is the correct answer to this part of question 6. All right, now we have a different question. We're not talking about electrochemistry. We're back to particle level reasoning and entropy. So here's some more comments about that. The value of delta S is greater than 0 for this reaction. Using particle level reasoning, explain why the entropy increases as the reaction progresses. So the student said, as the reaction proceeds, the temperature increases. I'm not really sure how they knew that. In fact, I don't even know if that's correct, but I'll go ahead and read on. This temperature increase causes the particles to have greater kinetic energy and become more disordered. The particles have more degrees of freedom and more microstates. So it's not about the language of entropy. It's that we have no evidence that the temperature is increasing as the reaction proceeds. So that's why their answer is incorrect. There is no evidence to suggest that the temperature is increasing. So what we have to do is let's go ahead and go back to the phases of matter. Focus on states of matter on the left side, and then compare this to states of matter on the right side. So I see aqueous particles on the left. I see a liquid on the right. I see aqueous on the right. Oh, there it is, the gas. Okay, so this is definitely increasing entropy. It's not about temperature. It's about the fact that we have gaseous particles being produced. Now you can mention things like degrees of freedom and microstates and number of arrangements and orientation. So the entropy change is positive because the aqueous reactants produce 2 moles of gas. And these gas particles are far more dispersed, occupy a greater number of microstates than the condensed phases. So the entropy of the products is greater than that of the reactants. So the student assumed that the temperature increases, but that was incorrect. All right, now another part of this is about delta G. The student claims that the reaction is thermodynamically favorable at all temperatures because delta S is positive and the reaction is endothermic. This is again from the 2024 AP Chemistry exam. Do you agree or disagree with the student's claim that this will be favorable at all temperatures? Student says, I disagree because endothermic reactions are not thermodynamically favorable. So that is not true. Endothermic reactions can become thermodynamically favorable under certain conditions, and that would be at a higher temperature or when the delta S is positive. So just a blanket statement that endothermic reactions are not thermodynamically favorable, that's not true. Now, if you do answer a question on the AP Chemistry exam about thermodynamic favorability, this is my advice. The first thing to do is to say that a reaction is thermodynamically favorable when delta G is negative. Make that clear, that you're telling the AP readers you know that delta G should be negative if a reaction is thermodynamically favorable. The next thing I would say is go ahead and write the equation. Delta G equals delta H minus T delta S. So you've talked about delta G being negative. It's thermodynamically favorable when delta G is negative. You've written the equation. The next thing to do is to connect the sign of delta H to the sign of delta G. And then similarly, connect the sign of delta S to the sign of delta G. So a negative delta H supports the favorability of a reaction. A positive delta S supports the favorability of a reaction. So I disagree with the student because they said it was favorable at all temperatures. They said that delta S is positive, but they also said the reaction is endothermic. I disagree because the reaction is endothermic. So delta H is actually positive, and a positive delta H does not support favorability. In fact, a reaction with a positive delta S and a positive delta H will only be favorable at high temperatures, not all temperatures. And you can see on the slide, these are the official scoring guidelines. So disagree. The reaction is endothermic and has a positive entropy change. It will only be favorable at high enough temperature such that the magnitude of negative T delta S is greater than that of delta H. And again, they're saying that delta G is negative when it's favorable. That's good. And for that to occur at all temperatures, then the reaction must be exothermic and have a positive entropy change. So again, you can look at the official scoring guidelines, but as I mentioned, make sure that you are clear. Say that delta G is negative for the reaction to be favorable. Write the Gibbs free energy equation and then talk about the sign of delta H and the sign of delta S that would support favorability. Now, if you're thinking, could we do another electrochemistry question? Yes. So let's go ahead and take care. This will be our last question in Unit 9 for this video. And this is from the 2024 AP Chemistry exam. Now, it says that we're doing something involving rhodium as a solid. Solid rhodium is plated or deposited on the surface. So I'm going to make sure that rhodium is a solid on the right side of the equation. It says oxygen gas is produced. I'm going to make sure that O2 gas is produced as a product. So I looked at first half reaction in the table and I did nothing to it. That second half reaction, I reversed it so I could get oxygen gas produced. I'm going to add them together and oops, that is not correct. What I did was I completely ignored the electrons. So what's wrong about that? This equation is not balanced in terms of the overall charge. So I see +3 on the left and I see +4 on the right. So I'm going to go ahead and take care of those electrons. Now 3 and 4, if I could get those to be 12, that would be great. So right now I have 3 electrons that are gained in the first half reaction. I have 4 electrons that are lost in the second half reaction. So I'm going to multiply the first one by 4, the second one by 3. So my coefficients become 4, 12, and 4. And then my coefficients become 6, 3, 12, and 12. Now I can cross off my electrons, and this is the correct answer to this part. The balanced net ionic equation is now balanced in terms of overall charge. I see +12 on the left, +12 on the right, and all of the atoms of rhodium and hydrogen and oxygen are balanced. All right, the next part of this has to do with the cell potential. There was one equation, which was the rhodium equation. We did not reverse it, we simply multiplied by 4. But you do not multiply the cell potential when you multiply the coefficients of a half reaction. So I see 0.80 volts for the rhodium, the one that I did not reverse. The other one that I did reverse, that was 1.23, but now that becomes negative 1.23. Again, multiplying the coefficients by 2 or 3 or 4, you do not change the cell potential. So I'm changing the sign because it was reversed, and that's it. So my answer would be positive 0.80 volts plus negative 1.23 volts, and that is negative 0.43 volts. Now the fact that the cell potential is negative means it is not thermodynamically favorable. So here comes our next question related to the fact that the cell potential is in fact negative. Based on your answer to Part D, Roman numeral 2, explain why this process requires the use of an external power source. Because the cell potential is negative, it means the reaction is not thermodynamically favorable. And now our last part of this question involves a conversion from 2.8 grams of rhodium into time. So it says calculate the length of time in seconds required to plate 2.8 grams of rhodium. So I'm going to go ahead and start with 2.8 grams. First, I'm going to convert from grams to moles using the information on the periodic table. There's the Faraday constant in connecting coulombs to moles. I'm going to write that down. And now I'm going to connect that to time. So it says 2 coulombs per second. That would be 2 amps, or 2 coulombs per second. I think I will put seconds on the top. Well, unfortunately, I did something wrong. Let's see if you can figure it out here. I went from grams to moles. I went from moles to coulombs. I went from coulombs to seconds. Now, if you're not sure exactly what I did wrong, It has to do with the fact that there is a difference between moles of rhodium and moles of electrons. And so I didn't make the connection between moles of rhodium and moles of electrons. Back to the half reactions. There's 3 moles of electrons for every 1 mole of rhodium. There's 3 moles of electrons for every 1 mole of rhodium. Now you might say, but couldn't that be like 4 moles of rhodium? Okay, that would be 12. It's still a 12 electrons to 4 moles of rhodium that would reduce to 3 to 1. So notice that I inserted a conversion factor that wasn't there before. So I went from moles of rhodium to coulombs, but those moles are different. Moles of rhodium is not the same as moles of electrons, and it's not a 1-to-1 ratio. So there's my conversion from grams to moles. Now there's my new corrected conversion that goes from moles of rhodium to moles of electrons. There's the Faraday constant going from moles of electrons to coulombs, and then finally from coulombs to seconds. So the incorrect answer that I had was 1300. But now that I'm multiplying by 3 moles of electrons for 1 mole of rhodium, it's not 1300, it's actually 3,900 seconds. So that is not only the correct answer to this question from the 2024 AP Chemistry exam, finishing that particular question means that now this is the end of the video. If you enjoyed this lesson, I invite you to like this video and subscribe to my YouTube channel. You can add your comments and questions below this video, and you can also email me with your comments and questions at APChemistryReviewAndPractice@gmail.com. Now, this is my last episode of AP Chemistry Review and Practice before you take the AP Chemistry exam. So thank you for letting me be your guide on the side as you strive toward that 5, and I hope that when you complete the AP Chemistry exam, you can feel a sense of pride and satisfaction that you gave your best effort. So good luck to everyone, and thanks for watching.